Muy buenos días tengan todos ustedes. Es para mí un privilegio formar parte del comité organizador y a la vez tener el honor de ser el maestro de ceremonias de la sesión de apertura de nuestro primer seminario virtual Aditiva Querétaro 2020, organizado por el Centro de Ingeniería y Desarrollo Industrial, CIDESI. Las actividades de este primer seminario que se abordarán en estos 2 días de trabajo, en lo que contaremos con la participación de distinguidos líderes nacionales y extranjeros en diferentes áreas de especialidad en la selección de materiales para manufactura aditiva, tecnologías de fabricación aditiva y procesamiento asistido por láser, procesos de impresión y sus aplicaciones para muy diversos sectores, abarcando también cuáles son los retos y paradigmas actuales que existen en este tipo de tecnologías, de tal suerte que la ciencia nos pueda guiar en gran parte la investigación hacia poder vencer los retos actuales de los procesos por fabricación aditiva por alambre y arco también. También contaremos durante estos 2 días, bueno, particularmente el día de hoy, con un foro de discusión, donde invitamos a 4 expertos nacionales, en los cuales podemos discutir lo que es el estatus actual de la manufactura aditiva en México y las nuevas tendencias dentro de Latinoamérica. A continuación, para mí es un honor presentar a nuestro anfitrión del evento, el doctor José Cruz Pineda Castillo, director general de CIDESI, para que nos haga el favor de compartir un mensaje, inaugure nuestro seminario virtual. Por favor, doctor José Cruz, le cedo la palabra.
Muchas gracias, doctor Alvarado. Sean ustedes muy bienvenidos a esta reunión, primer seminario Aditiva 2020. Muy buenos días a todos. Y quisiera muy en especial agradecer a todos nuestros invitados que nos honran con su participación a este importante evento. Es para mí, por supuesto, un honor poder estar bajo mi responsabilidad esta declaración inaugural de este importante evento que está iniciando. Pero antes de hacer esta declaración inaugural, quisiera expresar unas palabras con respecto a este tema que nos ocupa en este día. Seré muy breve porque este evento es muy importante y yo creo que todos ustedes tienen el entusiasmo y el deseo de iniciar lo antes posible. Quiero primero hacer una pequeña reseña histórica que de hecho me tocó vivir con respecto a la digitalización. Cuando estaba haciendo mis estudios doctorales, esto es ya entre el 80 y el 83, 1980, 1983. En esa época estaba iniciando el control digital directo por computadora. Estábamos iniciando todos los controles de robots manipuladores articulados. Estábamos desarrollando la visión por computadora como un elemento esencial para digitalizar imágenes, ya sea estáticas o en movimiento, que nos permitían darle un sensor visual, una visión, una vista a los robots. En esa época me tocó utilizar la primera PC que utilizábamos tanto yo como mis compañeros y profesores investigadores, que era la PDP-11, que la mayoría de ustedes muy jóvenes seguramente ni siquiera escucharon hablar. De ahí me tocó llevar a cabo en mi tesis doctoral una tesis pionera, de hecho, en llevar a cabo un movimiento, controles de movimiento robótico retroalimentados con la visión artificial. En ese tiempo no teníamos que desarrollar solo la teoría, teníamos que desarrollar también todo el equipo necesario para poder llevar a cabo nuestros propósitos que habían sido planteados en las tesis doctorales, la parte teórica, la parte experimental, la de principio y la de comprobación. Me tocó, por lo tanto, junto con mi asesor, desarrollar todo un sistema de visión de los primeros sistemas digitalizados por computadora para poderlo instalar y hacer la retroalimentación a este control de movimiento por un robot de varios grados de libertad. En esa época, entonces, iniciaba la digitalización. Mostraba una versatilidad impresionante, con muchos también retos y desafíos. Teníamos un problema importante en la estabilidad. Al digitalizar, cambia entonces la dinámica de los procesos, no la dinámica natural, sino la dinámica que se induce por la digitalización y produce problemas de estabilidad que hay que resolver y venían junto con la digitalización. Había problemas, por supuesto, de ruido que inducía la propia digitalización también, que había que resolver porque era también en su momento un desafío mayor. En ese tiempo también el control numérico de las máquinas que nos permitían maquinar superficies bastante complejas, también cuerpos tridimensionales con una cierta complejidad que fue aumentando. Me tocó llevar a cabo las primeras interpolaciones circulares con personal de FANUC, que en aquella época era todo un desafío. Ya las interpolaciones lineales eran un desafío, pues las circulares requerían una optimización por segmento, de segmentos de círculo. Fue todo un desafío en su momento. Me tocó llevar a cabo entonces el desarrollo del primer sistema de digitalización visual en el CIDESI-SECIHTI y formar el primer grupo de visión por computadora que nos procuraba un desafío interesante y muy innovador en visión por computadora y en todo lo que refería a control retroalimentado por visión. En esa época parecía que se habían resuelto muchos problemas y que habíamos avanzado bastante en la versatilidad de la digitalización. Me parecía muy interesante el ver entonces cuerpos tridimensionales maquinados, muy interesante. Se avanzó mucho en la digitalización y en la versatilidad. Vino el Internet. Un poquito antes del Internet, las comunicaciones digitales aparecieron un éxito fulgurante. Vimos cómo empezó a surgir lo que se convirtió en un sistema tecnológico revolucionario y fue la revolución digital Empezó en esa época el invierno, desafortunadamente el invierno de la inteligencia artificial por sus métodos heurísticos, que en su momento empezaron a sembrar cierta desconfianza, porque la heurística, sin un manejo suficientemente riguroso, nos lleva a producir inexactitudes y desafortunadamente a un comportamiento que parece aleatorio, que no lo es, simplemente es un comportamiento incierto por las muchas posibilidades a lo que nos lleva la heurística. Y por eso vino un invierno de la inteligencia artificial. Y posteriormente vino entonces el Internet, trayendo otra oleada fuertísima de digitalización y de comunicaciones. Se pudo observar que la digitalización era un camino fundamental para poder seguir desarrollando tecnologías de todo tipo, pero especialmente aquellas que son unificadoras de la ciencia y la tecnología. Y lo digital, junto con comunicaciones, información, control, cómputo y sus derivadas como inteligencia artificial, procesamiento de las señales, etcétera, lo que en su momento fue la cibernética como un nombre viejo al control general, se vio que eso nos daba una versatilidad y un potencial de unir disciplinas que aparentemente no podían unirse tecnológica y científicamente. Y entonces vino un progreso que en su momento no se había previsto con tanto desarrollo por la digitalización. Obviamente, en la mente de muchos conceptores muy visionarios, se fue plasmando esa posibilidad de desarrollo tecnológico tan importante, pero no necesariamente para todas las mentes que generalmente se vuelve usuario de estas tecnologías importantísimas. De golpe nos encontramos con los Cyber Physical Systems, con la comunicaciones M2M, con el Internet de las cosas, con las máquinas que pueden ser totalmente formales y estar solamente en una máquina emulando el comportamiento de otras máquinas, pero también estar insertas en una máquina física. Y entonces, tener un desarrollo autónomo extraordinario. Y entonces, después de esto, pudimos observar que había otras formas también de manufacturar, de maquinar, de producir. Y vino entonces la manufactura aditiva, la impresión tridimensional, con cambios también sumamente importantes. Si bien el control numérico nos permitía maquinar piezas muy complejas, o nos permite, y algunas que son muy difíciles de hacer de otra forma, si no es a través de un maquinado con un buen lenguaje que nos lleve a movimientos controlados numéricamente con mucha precisión. Se ha observado también la posibilidad de llevar a cabo una impresión tridimensional que puede ser muy ventajosa con respecto a esas tecnologías, pero además acarrear nuevos modos, nuevas formas, nuevos avances tecnológicos para llevar a cabo manufactura que no podíamos realizar tampoco con esas tecnologías, por muy avanzadas que considerábamos que estaban. No podíamos, por ejemplo, maquinar interiores complejos, que ahora es muy posible llevar a cabo. Y todas las ventajas y todas las formas que tiene la manufactura aditiva, que ustedes conocen muy bien, porque tenemos entre nosotros excelentes expertos y especialistas, y muchos de ustedes que están en este seminario, primer seminario virtual de Aditiva 2020, muchos de ustedes están ya con una iniciación en la que entienden mucho de lo que yo estoy hablando. Sin embargo, después de que nos encontramos con la manufactura aditiva, hemos observado que de lo que yo les platiqué, que estoy hablando de los 80, 83, 1980, 83, a la fecha, en manufactura aditiva y en todas las tecnologías digitales, flexibles, prometedoras, eficientes y excelentes para llevar a cabo desarrollos tecnológicos de muy avanzada, no tan solo para este tiempo, sino para el nuevo sistema de tecnologías digitales que se está imponiendo actualmente y que muy pronto estará instalado con todo su esplendor, y que le hemos dado por llamar la Industria 4 o la Cuarta Revolución Industrial, aunque podemos llamarle de muchas otras formas, puesto que una revolución, solo la historia lo dirá. Podemos contribuir a realizar algo, pero no la haremos hasta que la historia diga qué ocurrió. Pero lo que sí es seguro es que este nuevo sistema de tecnologías digitales que se está implementando, que se está imponiendo por él mismo, por su propio derecho, este es un sistema revolucionario. Y este sí va a producir una revolución tecnológica. No sé si una revolución industrial 4, pero sí aseguro que una revolución tecnológica, digital, y no como la que acabamos de terminar a través del Internet, sino una revolución tecnológica que va efectivamente a influenciar profundamente la actividad de la sociedad y la actividad industrial y lo que estamos por llamar también la Smart Manufacturing. Este hecho fundamental en el que estamos nos permite observar que desafortunadamente no hemos hecho una tradición tecnológica en México suficientemente importante. Una tradición de desarrolladores tecnológicos que estemos entonces previendo todo lo que hay que desarrollar tecnológicamente, al menos lo que concierne y lo que podamos hacer a nuestro alcance y nuestra posibilidad en este sistema de tecnologías digitales que se impone. Nuestra tradición, pequeña tradición tecnológica, está asociada a una pequeña tradición democrática, puesto que las políticas públicas tienen una influencia sumamente importante en los desarrollos de nuevas tecnologías si se trabajan en forma sinérgica para poder dar nuevos desarrollos conjuntos que permitan ser utilizados por la sociedad y muy en especial por la industria que es fundamental para el desarrollo económico de un país. Pero también el desarrollo, la tradición democrática es tan importante como el desarrollo económico o industrial de un país, porque de otra forma no se puede lograr esta sinergia. La democracia per se no es la solución, pero al menos permite el que se puedan discutir públicamente y más abiertamente los problemas que son fundamentales para un país y entonces desarrollarlos. Este tipo de reuniones y seminarios en verdad me da mucho gusto. Muestran que el tiempo es propicio para empezar a hacer una tradición de desarrollo tecnológico. Una tradición de desarrollo en la que estamos exactamente a un muy buen tiempo para desarrollar dentro del nuevo sistema de tecnologías digitales. Y por supuesto, la manufactura aditiva, la impresión 3D es clave en este nuevo sistema. Nuestros vecinos norteamericanos, ellos dicen que el desarrollo de un país, y en verdad me parece muy razonable, depende de 3 factores. Y dicen el desarrollo económico, el desarrollo de un país depende de la ciencia, depende de la tecnología y de la manufactura. Efectivamente, todos los procesos de transformación requieren manufactura, que requieren manufactura desde la entrada de la materia prima de la interacción entre las comunicaciones, entre máquinas, entre procesos, hasta que resulta un producto competitivo, un producto nuevo, un producto que se va a posicionar en el mercado y que por su calidad y rigurosidad científica, tecnológica, se puede manufacturar. Y si es con una manufactura avanzada y la flexibilidad de lo digital, entonces se vuelve compatible con todo el sistema de comunicación, de interacción entre máquinas, M2M, etcétera, y es clave entonces la manufactura aditiva, la impresión 3D. No les voy a hablar de todas las ventajas y características que tiene la manufactura y la impresión 3D, porque ustedes seguramente lo conocen y sería ocioso de mi parte estar repitiendo todos estos elementos que ustedes conocen muy bien. Sin embargo, yo creo y los exhorto a que este evento nos permita socializar tecnológicamente, nos permita intercambiar muchas ideas tecnológicas, nos permita también preparar nuestras mentes en este primer seminario, no tan solo a otros seminarios, sino preparar nuestras mentes a que lo que viene en el desarrollo de la tecnología, en el nuevo sistema digital, es un compromiso contraído ya por quienes están en el desarrollo tecnológico, en la investigación, en la industria, para poder empezar a crear una tradición, pero no tan solo una tradición, sino una generación de desarrolladores de nuevas tecnologías. Primero, entendiéndolas bien, asimilándolas bien, haciendo innovaciones incrementales de mejora y luego planeando a largo plazo hacer desarrollos disruptivos propios que puedan ponerse en el mercado internacional con un apoyo internacional, pero muy especialmente yo diría con una colaboración internacional. Actualmente ningún país ya se encuentra aislado. Un desarrollo tecnológico en un país afecta favorablemente a otros desarrollos tecnológicos, pero es sumamente importante que haya desarrollos que nos permitan estar de igual a igual, desarrollando e intercambiando y no solamente siendo usuarios tecnológicos para siempre, porque eso sí nos posiciona en una desventaja científica, tecnológica y de tradición de desarrolladores a un nivel que no debemos conservar en forma continua y repetitiva. Por tal motivo, yo les deseo mucho éxito en este evento importante, en este primer seminario de manufactura aditiva. Les deseo éxito para que haya un intercambio no tan solo de ideas, sino ya de compromisos de desarrollo, un intercambio de tecnología que nos permita entender, aprovechar al máximo lo que en este seminario nos enseñarán expertos en tecnología aditiva. Y con esto termino mis palabras, agradeciendo una vez más la presencia de todos aquellos que hemos invitado y que nos distinguen con su presencia y que son expertos en estas tecnologías, y a todos ustedes que se encuentran aquí con mucho optimismo, con mucho entusiasmo para intercambiar y para aprender. Por tal motivo, siendo las 9:25 del 1 de diciembre del 2020, declaro formalmente inaugurado el primer seminario Querétaro 2020, seminario de aditiva. Muchas gracias, un gusto y mucho éxito.
Muchísimas gracias. Agradecemos la intervención del doctor José Cruz Pineda para dar este pasaje a través del tiempo sobre la evolución y la llegada de estas nuevas tecnologías denominadas dentro de la industria 4.0 y cómo México está en un momento adecuado para empezar a tomar un rol importante y protagonista dentro del mismo. Muchísimas gracias. Finalmente, y no me resta más que en nombre del comité organizador agradecer a todos nuestros ponentes, a las personas que se encuentran actualmente en línea registradas de México y de otros países. Muchas gracias por su atención, agradecemos su presencia en esta ceremonia. Cualquier duda sobre los horarios y ponencias están disponibles en nuestra página www.cidesi.com/aditiva/. Ahora vamos a switchar un poco al inglés para introducir a nuestro primer ponente. Then we invite you to continue connected to be part of our plenary lecture by your guest, Dr. Andrei Bobodin, Professor of the Department of Material Science and Engineering in the College of Engineering at the University of North Texas, UNT. Dr. Bobodin holds a PhD in Material Science from Tula State Technical University in Russia. From 1994 to 2015, Dr. Bobodin worked in the Air Force Research Laboratory, where he was a principal research scientist and team leader for tribology, thermal management, and nanoelectronics materials of many different research teams. Dr. Bobodin holds several U.S. Air Force awards for her excellence, and all the time he spent there, he has, till he joined UNT in 2015 as the Material Science and Engineering Department as a chair, and later his current position is the Associate Dean of Research at the same university. Dr. Bobodin continues his research in thin films deposition, plasma-assisted processes, surface engineering, in situ process diagnosis, tribology, electronic materials, and additive manufacturing. Dr. Bobodin has over 300 technical publications, 1 book, 8 book chapters, more than about 12 patents and inventions. His work has been cited about 12,000 times, and he advised and graduated 20 PhD students and 5 master students. Andrei is a long-time ABS Science and Technology of Materials Interfaces and Processing Society member associated with the Advanced Surface Engineering Division, and he has been a fellow since 2010. Muchas gracias, Dr. Andrei Bobodin, for accompanying us in this ceremony and to be the first lecture in this virtual seminar. Then I give you the floor to start your lecture. Thank you so much for your time, and I invite all the assistants to enjoy this very interesting lecture. Thank you, Professor Bobodin. The floor is yours.
Thank you, Dr. Alvaro, and thank you all my friends in the CIDESI and the colleagues with whom I had the privilege interfacing and visiting some time ago, and we actually reverse visit to UNT, so we have long time collaborative work. I'm glad to present today. Of course, in other circumstances, we will have the in-person meetings, but I had the pleasure to connect by virtual platform and update on the research which is going on in the University of North Texas, as well as present some research and maybe can spark some of the future ideas for the collaborative work and advancing the science and additive manufacturing and the surface engineering. This is my area of the research. Thank you for the organizing committee extending to me, inviting me for this, give the seminars in here. And it is a pleasure of mine to provide for you. I will share the screen with you in a moment, and in the end, I will be very happy to answer the questions. So that's starting the sharing screen, putting on a little larger. All right, so I hope that everyone can see the full screen in here. The title of my talk is talk about laser assisted processing and additive manufacturing technologies. Before I'll start, I acknowledge the contributors to this talk, and those are my students up front. Ben Sirota, he graduated last year and he's now at the Intel Corporation. Dr. Nick Glavin is my former student. He's working in Air Force Research Lab. Corey Arnold is my current PhD student working on some of this 2D material processing, and Dave Flannery is working on with me on in situ monitoring of additive manufacturing. I have also my colleagues, Raj Banerjee and Dr. Narendra Dahotre, who are involved in additive manufacturing in here. The results which I'm presenting, the result, of course, the teamwork, and I'm the presenter of this. Just to give you some updates, very recently, and here at UNT, we established the Center for Agile and Adaptive Additive Manufacturing. And this is under the 10 million legislative support from state of Texas, which has identified the UNT as one of the prime locations to advance additive manufacturing technologies, particularly focusing on functional material processing as well as metal processing. We have a range of the equipment which has just been recently bought and in process for installation. Some of them already in here, and some of them incoming this, as we speak. So this is a brand new center with new facilities and new equipment, and we extend to our colleagues in the CIDESI to connect with us and discuss what additional opportunities those bring. You can see here pictorially that we have fusion systems, so we have jet binding systems. We have very interesting end scribe system, which allows for that micro milling pick and place for microelectronics additive manufacturing. And then we have more like a standard system, like a laser powder bed fusion system, but it is a research grade accounting system, allows a very high flexibility. Of course, have some laser mill, selected laser mill system. The Optimec lens, which is on the right side in here, has a 4 powder hoppers, and I will present some results from this machine. We had it for more than a decade working in this area. And then we are adding those additional systems which are shown in the bottom here for both metal, but also for the polymers. Importantly, also, our faculty has strong research in modifying and developing the new alloys for the additive manufacturing. So that's why the equipment for raw handling powders is incoming for the plasma treatment. So this is the plug-in from the center. And this is combined with the facilities which we had also in coating and thin film deposition area, which is one of my area of the expertise, working with thin film for a number of years, where we have machines from the sputtering to beam evaporations to ALD, atomic layer depositions, and chemical vapor deposition. And we're combining some of those together in those additive manufacturing approaches, especially for the functional material devices and the sintering, which we'll build on. And I wanted to bring it to your attention, this facility, as a note, as mentioned, that we worked for years now with one and a group in CIDESI, and we'll be glad to extend maybe potential additional research projects and ideas. All right, so now coming back to my talk. So I will talk today in 2 areas. And one area is related to the additive manufacturing of the functional material device fabrication with the 2D materials, 2-dimensional materials. And this is the combination of the sputtering, thin film growth, and the laser annealing with the direct writing, which has enabled us a direct fabrication of that semiconductor devices using the 2D materials approaches, avoiding any of the pick and transfer in place. So it's basically direct production. So, and this is maybe some of the non-traditional area for additive manufacturing if you think about the component building. But this is rapidly expanding the area in functional material devices, and we're looking at very, very closely to that. Well, and the second one, it is a little more traditional in terms of the platform using. So we'll talk about laser sintering alloys during laser engineering and shaping or lens. But it is not necessarily the talk will be not here focusing on how we do this. It will be focusing more on in situ diagnostic of the process and specifically on a chemical composition diagnostic, which enables us for the gradient alloy fabrication. So there's the 2 parts of the talk in here. I will time myself so I can complete that in all during the time of the seminar and answer the question. All right, so let's start with the first one. Just a brief reminder about the 2D materials. The 2D materials, the ones which are monolayer in the thickness, and therefore they allow a host of very interesting the physical as well as the mechanical properties. In physical properties, of course, this is the confinement of the charge carriers. And if you take the graphene on the left chart, of course, you can have electrons, you can confining, and thus you have very interesting physical properties, which is lead to the host of the applications ranging from the computation because of the very high speed. So on the left chart here and below, you can see a comparison of the mobility for the charge transfer, and also different type of materials which is electronic communities using, like polycrystalline silicon, for example, or you can see some other carbon nanotubes, etc. And then you can see that the graphene is absolute winner in terms of how fast the charge carrier can be transferred. So therefore, there's also a lot of their interest in terms that high-speed computing and using that. Of course, there is some other interesting properties, and anisotropy of the thermal property propagation, for example, is another very interesting feature of the graphene and monolayer. Since that Nobel Prize have been awarded for the extraction of graphene and showing the physical properties of that, that gives the impact to a host of the 2D material development, where you can have a range of the semiconducting to the insulating. So if you go on the right side here, you have band gap all the way to the 6 electron volt. So this is hexagonal boron nitride is the insulator material, which is extracted in 2D form. And then in between, there is a group of the semiconducting material where the band gap can be engineered anyway from 0 to a few electron volts. One of the group is very dominant present is dichalcogenides. And dichalcogenides consist of the metal atoms and the sulfur or selenium atoms attached on the top and bottom here, but there's also still one monolayer because within this group we have strong covalent bonding, and then outside there is almost no bonding in there, which is again gives us that very interesting properties of confinement. But now we can confine both electrons and holes and make N-type and P-type semiconductors. And because they're very thin, they allow us very interesting property for the direct band gap leading to the photovoltaic and basically solar to energy light conversion. But because of the very thin, they also have very good mechanical properties. And I'm using this, the right figure here from the Jackie Wander paper on the review on the 2D materials, which is showing us inherent flexibility of these 2D materials. And because they're very thin, they can sustain very high degrees of the strains, which is very interesting because now you can think about it, making those devices embedded with the clothes, with the wearable devices, or even attach it to the human body as a sensor, and they will breathe and they will expand and contract as we're using that while still doing the functional research. So the question is really become, okay, there's a lot of interest how we can make them and how we can make them cost effectively and not the way how it was, extracted before with the scotch tape techniques or with some others. And there are some challenges along that way. We're still in the 2D community who focusing on that. There is a challenge here, and I will show you maybe some of the advanced ways in here. So the challenge which is maybe facing the 2D community in terms of fabrication and using them on the devices is the production at larger scale and low temperatures. And the problem is that if you follow the literature on this 2D materials fabrication, they will find out that most of the processes, like 90% of them, will use high temperature growth. And the CVD, chemical vapor deposition, is one of the most popular technique where you take the gases and can be carbon containing gases and feed them into the tube furnaces, have a catalyst there, and at 800, 900 C, the gases decompose and you start forming the graphene if you're using the copper nickel substrate. Or you can can grow molybdenum disulfide or tungsten diselenite if you're using them sulfur and selenium additions and using the metals. But also high temperatures lead to the crystalline growth, and they are growing in this layered formation as shown here, as fulminate layer thick molybdenum disulfide on a sapphire substrate. And if you look on a planar view, if you look on from the top of that, then you will notice that they'll nucleate and grow as perfect crystals, in this case are triangular shaped crystals, and they will pop up and start spreading until they cover the entire surface. Well, now imagine you try to make a transistor out of this, and if your surface is not completely covered, so that many crystals are not get joined, then you can run into a situation when you have a gap into your channel because you happen to be right over here, right? So, and it's a challenge, how you can do them uniformly. Of course, there's a lot of progress being done in that area, which is trying to make those crystals larger. Because the danger is that if you just let it go over the time until everything covered, it's also growing the thickness. And once you get in the thickness more than a few monolayers, you start losing all these advantages of the charge confinement. So then it's all ideas that disappear why you want to do it. So it is, but even now, when the community can now grow fairly larger crystals in here, it's a still very high temperature growth. So that's meaning, you know, you cannot really put directly on the polymers anything that's stretchable. So yes, you have to do flexible material, but you confine by the fabrication process to put them on something like a silicon wafer or something like temperature stable, not really directly on the polymer. All right, so what's the way around it? Well, in one of the things, and I was during my time when I was working in an Air Force Research Lab before joining UNT, we came across that idea, how about we start using a PVD, physical vapor deposition, and not chemical vapor deposition, for growth of the film. An advantage of physical vapor deposition that you can use the energy of the plasma, which is once you're sputtering a given argon, you also generate a high energetic atoms sputtering from the target, say it's a molybdenum disulfide, it will be molybdenum sulfur. And those that have high energies can be between 1 to 100 eV, which is you can use to organize the structures on the surface and not necessarily bring it up the temperature. So you start dropping temperature down, and you can still produce those 2D materials by PVD. And this is an example on a silicon oxide growth layer of 2D amounts to just few monolayers thick. And this that decouples that from the CVD. And fundamentally, the PVD is using high density flux, so you have high deposition flux and high energy, kinetic energy. Or chemical vapor deposition, you're using low density flux and low incoming kinetic energy by high temperature. So in the CVD, you're using the temperature for atoms to hop around, find a place and form the crystal, that crystal grow. On the PVD, you don't allow for that time. You bombard them with a lot of the atoms. Those atoms have very short time to move around, and they're locked in place. And if the temperature is too low, they will produce amorphous material. So the temperature a little bit high, you have enough of the energy, they will form the nanocrystals. They will rarely or almost never will grow the single crystal unless the temperature is too high. So low temperature, that's what it is. So this kind of a constant process of both and here. One of the things which you need to watch for these processes with the kinetic energies is the formation of the defects in crystal lattices. If we work for 2D molybdenum disulfide and want to fabricate it this way, and we're using the high energy to bring the atoms and form them, well, the atoms also can have enough energy to knock out the sulfur and become a sulfur vacancy, and vacancy in the presence of oxygen can be filled with oxygen there. So you can create the defects of vacancy or creating oxygen incorporation. So you need to watch out. So this takes about 8 eV of energy to create a vacancy to tweak the process. You also, over the time, you learn how to control the growth in the direct growth deposition. So making 002 and making planar surface parallel. And then how do you reduce the defect formation by controlling argon and bombardment. And then keep the stoichiometry. Sulfur is easily to combine with oxygen, hydrogen, and be evacuated from a vacuum chamber. So keeping moly to sulfur 1:2 ratio is important to achieve the electronic properties. So, and that was also learning through that. So in terms of how does this whole process work, so you have a substrate on the bottom, you have a target right on the top, is on here, oh sorry, right on the left on here, the molybdenum disulfide target, and it's you switched on and you sputter a molybdenum disulfide, which is directly depositing in here, and it grows for a few seconds and you're done. Process takes just a few seconds, and then you need to analyze it. For analysis, we're using the Raman spectrometer, which is very sensitive to breathing modes or vibrations in molybdenum disulfide in planar and in perpendicular direction. So because this is two primary vibration modes, they will appear in a Raman signal as a two peaks. So you can have in plane and out of plane vibration peaks. And interestingly, that peak position relative to each other, the distance between that in plane and out of plane vibrations will depend on how many monolayers you have. And therefore, by measuring the distance from one peak to another, you can actually measure how many monolayers you produce. You don't have to do the TEM then and wait for the destructive. You can do in situ analysis what you produced. All right, so the process then looks like this. And this is, see if the movie we play. Here. My apology. Maybe in the end of the talk, I will try to play it one more time. But in essentially the sputtering, and then we have a Raman signal as a check-in on that. And I will see during the question and answers, maybe I can dig out that movie and play it. Apology for that. But if you will grow this on that, so we will produce those few monolayers thickening here. This has some interactions in the grain boundaries, which is slow down the charge transfer, which is for the high-speed computing is of course problem. But if you're doing the sensors application, you're not concerning about how fast the charges are moving in here, then that's just not a problem at all. But advantage of that, we can start dropping the temperature down. And now ultimately, if we drop the temperature all the way down and we want to produce these fabricated devices on a polymer substrate directly, then the temperature is not enough to make any of the crystalline materials at all. So you'll lock atoms in place where they arrive. They don't have anything ability to hop around and form a crystal. You make amorphous material. And then this is where the combination with the laser comes very, very useful. Producing amorphous film then by PVD methods and room temperature on any polymer substrate, and then bringing lasers to anneal during annealing, depositing the energy on these 2D materials on that very thin amorphous materials produced, it converts it to 2D material crystalline, where you put the energy on of the laser. And that's then leads to direct rating of hexagonal or crystalline material on amorphous material. And from physical properties perspective, the amorphous materials is insulating, and crystalline is a semiconducting material. And so essentially you can write a semiconductor channels within the insulator. And this leads to then a device fabrication in direct way. So then the process became a two-step. So the step one, you use few seconds growth, and it's really like we talk about 60 to 120 seconds deposition time. We're using the PVD sputtering of molybdenum disulfide, and you can cover as large area as you wish. It's all amorphous. You can do in plane here. You can have moving the targets. You can do the roll of the polymer film. It's because you're producing on room temperature. There is no requirement for the heating of the substrate. Everything becomes very simple, and it is very quick. Again, we talk about 60 to 120 second deposition time. And once you're producing it, it's amorphous. So that's meaning if you shine the Raman laser on that, you will have the black curve, no peaks, no in plane and out of plane vibrations, because there is no crystallinity. And only after a laser annealing, you'll form the hexagonal materials and you start seeing the peaks appearing in here. So in terms of growth, when you're growing on a flexible polymer PDMS structure, which is stretchable polymer, after you grow that and take it out of the vacuum chamber, the polymer shrinks because in vacuum it expands, and once you're getting out of the vacuum, it shrinks. So showing the corrugating structures in here, this is the surface of the film on a polymer gets shrank and showing that. And at first we thought, okay, could be the problem. But then we found it's not a problem at all, because we're talking about just few monolayer film production of the semiconducting, and because it's conformal and flexible, it is just covering this perfectly. And in fact, after being shrunk, you can also stretch it. So you can have very high degree of stretching that polymer and it still be operational. All right. So in terms of annealing and powder, of course, there was a lot of the experimentations on that. What's the optimal annealing power needs to be, how much energy deposit, is it a wavelength dependence on that? And we found that there's actually very little wavelength dependence, but quite a bit of dependence on the density of the power you need to put per unit of the area to anneal, because you want to find that balance, converting it to crystalline material, but not destroying it by ablation or other heating. And during that process, you're also concerned, if you're doing an air, how much oxygen of you intaking, because you take molybdenum disulfide, you want annealing it to the crystalline, but if you're doing it in an atmosphere, then you can also ambient environment, and oxygen will come and react with the moly. So you can see XPS, X-ray photoelectron spectroscopy spectrum, which is showing the intake of moly oxide formation during the annealing. So as deposited, you don't see much of the moly oxide peaks, mostly molybdenum disulfide. And then as you're annealing, you start seeing that molybdenum oxide peak starts appearing. Again, this was done in air. And there is a ways around, of course, of that. You can think about annealing in the inert environment, which is as to the cost of the production process, right? So we try to avoid that thing. Or you can start thinking about annealing under wide band gap materials, which I'll talk about in a moment. So this is some experiments are shown in here, and in comparison as deposited and annealed on a PDMS substrate. So in the previous chart here was on silicon, and here this is on a stretchable polymer substrate. And as deposited is amorphous after annealing, and you can barely see then annealing in optical, but if you look on the Raman, you'll see that it is definitely the crystalline material shows up in here. And of course, it is annealing only occurs where you deposit in the light. And therefore, as you draw that lines, this is only within these lines when you do the crystalline. And between is amorphous, it's insulated. So essentially, you can grow the semiconducting channels with this insulator. And it's showing that laser mapping technique showing this channels productions in here on a molybdenum disulfide. And if we'll do the TEM analysis, then as deposited as amorphous, if to focus on that one channel anneal it, you see well-developed hexagonal structure of the material formed in here. So you can convince yourself, okay, that's during this annealing, right over here, I made that hexagonal material semiconducting. That group which is working in Air Force Research Laboratory, they continue to optimize the process, and this is work by Dr. Nick Glavin and his team who are advancing this process to the next level up using this very highly sophisticated combinatorial analysis method, which would pair it to autonomous experimental planning. Essentially, they're using the silicon pillar wafers in here, And each of the surface of the pillars, and there's hundreds of thousands of them manufacturing by lithography techniques on silicon. So each of the surface is one experiment. And the way how that autonomous experiments work, that the machine is programmed to deposit the heat of the laser on the surface to bring the temperature up by annealing, and monitor the temperature by laser shift, and then check that in-plane and out-of-plane vibration for the crystallinity. And then the machine is set to find the optimum parameter by varying the gases composition or varying the power of the laser. And that's those an autonomous way, running multiple hundreds and thousands of experiments, and then self-guiding itself to achieve the highest sharpness of this in-plane, out-of-plane vibration, which just gives you the highest crystallinity. And that's experiments then related to the optimization of the annealing parameters. Okay, what the power, what the time is on this type of the conditions. And as a result of this very interesting work, again, you can see that citations in here. I advise you to follow on that. This is work by Dr. Glavin and his team. That it is possible then to see that reduced defect density and increasing atomic order as you're heating up that locally. Now the local heat is only holding for the few seconds in there, so there is a challenge that is deposit with the less substrate damaging if you're using the polymer substrate and non-silicon oxide. All right, so moving on in here. So if you're not doing a flexible substitute in here, and it was demonstrated that we can do molybdenum disulfate, you can also do the heterostructures. You can grow molybdenum disulfate and tungsten disulfate as a bilayer structure and anneal it. You can also anneal it under the boron nitride, which is one bang up material. And those is leading now to the engineering of the entire device, where you can have a semiconducting layer. You can also have boron nitride, which is a very good insulator dielectric material, and those leads to the direct device fabrication. And because now you're not bounded by temperature of the substrate, you can do the polymer substrate for the growth of this amorphous materials by sputtering and using laser annealing, then for a very short time, not damaging the polymer, optimized just to anneal it for the semiconducting channel. And show the some of those results along this way. So this is one is actually coming from my group. This is done by my former student, Ben Sirota, working with me, where we, as deposited is basically insulator, as anneal it, it shows that some current flow because it became a semiconducting. It is maintaining the flexibility, and we are using this separation in between these two gold electrons, and where we're measuring all its electrical properties. And then the process is became like this. So we're taking the PDM substrate, sputter molybdenum disulfate, laser anneal it, so we can have semiconducting channel. Now we have semiconducting channel right over here. Next step is deposit with E-beam lithography, evaporation of source drain contacts. Then we put a gate that can be boron nitride, in this case, aluminum oxide made by ALD. And now we can have a top gate, and here we have a device directly fabricated on PDMS structures without any of the lift-off techniques using. And then we demonstrated we can have a top-gated molybdenum disulfate field effect transistor on the PDMS made this way. This is our molybdenum disulfate, which is laser annealed, and this is our the gate, in this case aluminum oxide, and there's a switching behavior of this as relative to the transistor operation. Now the transistor is one application, but another one is a sensors application, and you know, with the pandemics in here, there's a lot of interest to the sensors for the COVID-19. And here I would like to present to you the work of my longtime collaborator of Christian Muratori and his wife, Melanie Muratori, who happens to be in biology by expertise, and Chris Muratori is in thin film and growth technologies. And so they, two of them, over that spring lockdown time when we all were sitting at home and were forced to get out of the labs, they get together and think about how we can use that, the 2D materials, molybdenum disulfide, for COVID-19 sensing. And they came out with this, and that paper was just published in Journal of Vacuum Science and Technology. Chris is also a long-time AVS member as myself. So, and I advise you to take a look at it. It is a great review of the COVID-19 sensors based on this silicon 2D materials. And they also bring you this idea, which they realized. So that molybdenum disulfide, which is, we just talked about how it is produced with laser annealing, can be then functionalize it with the attachment of the antigen segments in here, which is active to that COVID-19 virus presence. And the idea is that this antigens, this is like antibodies in our in ours when we have a COVID-19 virus in the blood, that this antigens and antibodies react, and they are seeking for that, and they have that groups here through the peptide, the connections in here, which can be connected to that. So if you have this antigens attached to the sulfur, and it happens to be quite possible because of the sulfur linkages reacting to that, then they're sitting there and just waiting when the virus will come around. And as soon as this comes, it connects here, and this moment the charge transfer happens between the virus and the molybdenum disulfide, and this will affect the resistivity of that entire breach, which is instantaneously tells you that, okay, I can detect the virus. And it happened, the sensitivity is very high of this approach, and then they were able to demonstrate this in making a device. They also found that instead of using the entire antigen, like in all this assembly shown in here, it is better to use a fragmented one, so you can bring the charge transfer from that COVID-19 virus group somewhere in here, so that charge transfer and connections here, so that the shorter the pathway, the easier, the higher the sensitivity will be. And they were demonstrated that this can have, you know, very good parts per billions in sensitivities, and here you see here that, and you can signal in the millivolts as a response. And that happens to be that you don't, for this, you can have a synthetic antibody mimic protein, so you can actually manufacture them in a very scalable way, that functional things in here. And then there's specifically the protein from AC2 enzyme is in amino acids and very easily to bind to the sulfurs in here through the sulfur linkages. And then other side is a B receptor for the COVID-19 is in here to use as a detector that is connecting. So, and it was demonstrated working, and it's then become a simple resistivity check that, okay, and then if the resistance is off, then you're showing, okay, this is a positive, and this is the COVID-19 is in here in the presence. So they're working through this FDA approval and trying to scale up the technique right now. But again, I point you to this paper. But I wanted to show that as a good example of that, how we can use this additive manufacturing laser annealed molybdenum disulfide device in the current situation for them as sensing. Okay, so watching my times in here, and I'm moving to that second part of my talk, and we'll talk about the spectroscopy approaches. And this is now more the traditional additive manufacturing platform. We'll be using laser engineering and shaping of lens. We're using the laser and the metal powders, but we'll be focusing on the spectroscopy tool for the in situ diagnostic, which is I'm working with my students at this moment and understand how we can get that parameter. Okay, kind of reminded, and it's a very basic, and just to show you where the area we focus on. Of course, you have powders in here, you're breathing the high energy laser, you're melting, you're forming the melt pool, which is you're scanning, and you sinter your part this way. And during this process, you have quite a lot of the energies in here, and you are releasing some of this energy through the plasma emission, which is basically ionization of the vapor material near proximity of the metal pool by incoming laser. And then once that ionized species go back to the ground states or less excited state, they emit characteristic light that radiate light is coming out. And that characteristic light is very specific to what it is type of vapor is present right on the surface of the melt pool. Well, if you have the powder of different composition, aluminum, titanium, etc., vanadium, then you can expect that characteristic light will contain that wavelengths of that particular elements. And if you start varying these elements and their concentrations, then the expectation that the light emitted will be here proportional in intensities to a number of that atoms or elements of this present. And this is that ideas that using non-destructive spectroscopy of radiated emission used by the working laser as basically a fingerprint to look on the peaks in here, analyze them, and see if we can use it for elemental composition monitoring of the melt pool. Which is, if you have no variations, of course, maybe not of the interest unless you start losing some low melting point materials such as aluminum and you want to compensate for that. But for the gradient composition, the processes where you have a direct feeding, such as lens system, when you have using the nozzles to bring the powders, and in your hoppers here, you can vary the powder, so you can vary the elemental compositions in here. Then for that process, that's direct feedback. Okay, what chemistry is in here? Maybe a very of the interest, of the practical interest, and from the perspective, you know, adjusting it from a perspective, what if one of these nozzles get clogged and you don't deliver one of the powder ingredient and you want to compensate for that, or you want to at least know that. So from those process stability as well as making the complex gradient parts, that's we're interested in that. So objective is, can we extract information on chemical composition in the work zone by monitoring the light? Okay, I'm sure there are some of the initial results which we have in here. Before showing the spectroscopy results, I'll show you that we're using the Optimac lens 750 system. I mentioned we had it for more than a decade. Dr. Raj Banerjee is working with this, and that system is modified with 4 powder hoppers. So you have 4 nozzles, so that you look inside of this chamber, and it's inside of the glove box, so it's under controlled environment argon. That's as a laser column. You come in here to the nozzle. If you zoom into the nozzle, you can, this is the 4 nozzles which is deliver the powders. A laser coming through that, so infrared laser 1 micron 0.64 coming in here and heating it. And right in here, you can see some glowing in here. That's the plasma. You look through that, and depending on the laser power, it can be more bright or less brighter. On the right side, this is where you start collecting the lights in here. So this is a fairly standard way to arranging. The only thing which we added here is the light collection assembly here, which I'll focus a little bit more detail. So for the light collection from that melt pool location here, we're using the collimating tube, which is essentially a known diameter, the pipe in here. We have a lens in here, and this way we protect the lens from the powder being deposited on it and changing that intensity of the signal. And then that lens is focusing it on a fiber optic, and fiber optic is then taking that signal out to the spectrometer. We're using the ocean flame spectrometers in here. Of course, we need to calibrate it to make sure that we are taking the light from melt pool here and essentially just above it from the vapor. And then we're using some of the laser guiding techniques to basically make sure that the place where we're collecting the signal is correspond to our working zone. All right, so what type of signal now we're getting? So once we start looking at it, and here it is the full spectrum from UV all the way to near IR and a region here to 800. So this through the visible range in here. So, and you can see here that we, first of all, yes, we can start seeing some peaks and appearing, but we also notice it right away that we have a lot of the background radiation because we're also heating the melting pool and we are emitting all of the white light in all the continuous spectrum. We also have a bremsstrahlung radiation, which is recombinations of electrons with the gas ionizations in here. And what we found that the region of the visible light to infrared is very highly dynamic and very hard for us to focus. Is going sometimes off the chart, sometimes go down, and it is going into that during the process itself. So it is go up and down in intensity very rapidly as it hits or not hit different powders into the laser beam. So we're then looking on a UV region, which seems to be a little bit less affected by that wide body radiation, which we see more visible in infrared. So in UV region, then we can start seeing some individual peak and structures, and we start looking on that particularly the nickel peaks analysis. And the characteristic wavelength, there's some peak overlap, which we had to work with because the multiple lines can be excited simultaneously. But we can, the good part was that we can detect some structure in emission and we can correlate them to characteristic peak. All right, so about the central peak location and the measurements has certain uncertainty because of the overlap. And this is something we're working with this, some of the methods, how to do this in an autonomous way. And then another observation that the data itself is very dynamic. So this is an example of sintering iron and nickel mixed composition powder. Those are peaks are present and here belong to iron and nickel, but what I'll bring to your attention that lines in here, how they offset on relative intensity. And also during the same experiment, so there's the same powder composition, and we take data within 80 millisecond intervals, so very short intervals, and you can see here the spectrum has shifted dramatically on this scale. So it is create also that additional challenge in how you can compare that during the time if your intensity is varying. So you need to have some common background extraction method for the comparison. So it is not that simple, and I think it's all comes because of later additive manufacturing. It's very the dynamic process by itself because you're sintering powders. Powders have different sizes, distributions, and that's all affects the plasma signal. All right, well, nevertheless, I said, okay, we'll try to do it on a gradient experiment and see if we can correlate some of the gradation of the powder feeding to the gradation of this intensity line, which we're detecting. So we made this experimental setup for the fabrication of iron nickel sample. And that particular schematic build was we're starting with the powder feeding in the bottom up. And first we have iron rich and less nickel, then we add more nickel and less iron, and then we finish with even more nickel, 45% nickel and 55% iron. So it's kind of model system in iron nickel system where we go when we know what powder we're feeding in the nozzles, and therefore we can correlate to the spectral signal from iron and nickel characteristics peak. We also did EDX post-build EDX analysis to actually correlate that, we're feeding the powders with this composition. We actually, that's what we see in iron, and that's what we see in the nickel in terms of the production after it's done. So that's looking onto the element distribution. So after we took the sample and cross-section that was the bottom, that was on the top. As we go from the bottom to the top, we're increasing the iron and we're dropping down the nickel because we are changing the powder feeding. We're also seeing the sum of the morphology and more the porosity development in here as we're increasing more of the iron towards the top builds in here. But in this experiment, we were focusing most on the composition, and because again, objective was to correlate to the spectroscopy signal. All right, so what we see in terms of spectroscopy. So when we take in the light, and we take in the light during the three regions, near bottom, midway, and finishing up the sample, we have multiple spectrum taken, averaging them out. we see, for example, for iron, this characteristics peak, and this is all in UV region here, the 221 nanometers. Now, the numerators here, 2 and 1, is in spectroscopic nomination. The 2 meaning the single ionized, the 1 is meaning excited atom. And so, and after excitation, is go to ground state and emit that light, for example. What we see here on the right is that, okay, do we see that characteristic peaks during all the builds? And, you know, sometimes we see them only in one region, and then for some, like 5.2, for example, we see it consistently during all of the entire process in here. So we picked up that lines in here, which we see consistently for the correlation to the chemical composition. Okay. And that's what we see. So we're increasing the iron as we build, and this is our spectroscopic signal. And we can see that intensity, or relative intensity of the peak after correlating for the background is also trending higher. However, we also see a lot of the data scattering. You can see here the huge data scattering here. And this is due to uncertainty of background correction, uncertainty of the peak location, and uncertainty of overlap. So these are the challenges with our spectroscopy additive manufacturing method, that we need to find the algorithms and ways how to reduce these uncertainties and how to make this that error bars much less. Trend is there, but it is not yet being much of the usable, I will say, in this point, for any of the process control or looping until we reduce the scatter of the data in spectroscopy. All right, so looking at nickel peak, we also find those characteristic nickel peaks that they're well comparing to the NIST databases for the nickel excitation. And again, that excited peak seems to be appearing, and there's few others appearing through all the regions. When we plotted the nickel peak, and our error bars getting even larger. So from that perspective, we are changing the nickel composition here, and we don't see much of we'll say a spectroscopic signal within the error bars and stay flat. So we cannot conclude anything, okay, either increasing or decreasing on nickel peak, even we know that during the build, we were changing the nickel composition as we go. So from that coming then my concluding notes, and that on the first part, in the semiconductor metal additive manufacturing processing with lasers, I think we have a great progress, and we in a point that we demonstrated that using this room temperature physical vapor deposition with amorphous material growth and then laser annealing is a very good way to directly fabricate semiconducting materials on the polymers. And therefore, we're advancing with that, and to make first devices, and showing the transistors, also showing you some sensors. We are very excited about one of this machine which is incoming now UNT installation called Nscribe, because it allows also to combine this method with the pick and place of the some elements, so we can build the entire circuits then, so that we can do this manufacturing in all steps. Now, on the second part in situ spectroscopy, I showed that way of where we are advancing for that, but also showed that there's quite a big of challenges which we see to overcome for the spectroscopy in situ for elemental composition. And this is due to the dynamic nature of the additive manufacturing process itself, the signal variance, the uncertainty in the background, peaks overlap. I think everything is possible to overcome with the modern techniques. Right now we are talking to our computer sciences and engineers, trying to bring some machine learning ways for the data analysis to extract this information on the fly from large subsets of the data which we're capturing. So it is definitely warrants through the research work. Are we there yet? I wouldn't say not in this time, but it is work in progress, which I'd like, glad to share it with you, and maybe it will spark some conversations and along these lines as well. All right, this is the conclusion of my talk, and thank you very much for listening, and I'm open for the questions to any of the chats here.
Thank you very much, Andre, for this interesting talk. Always a pleasure to have you here in this kind of events. Now, the seminar is open for questions. Please, anyone? Well, I have a couple of questions in case there's no, let's say, chat. I think they are still thinking. Well, I have a couple of questions. Let's begin. What about we have this kind of 2D and 3D printing concepts. I don't know if you say it so clearly and open. I think at the end of the first part of your talk, you mentioned a little bit of 2D printing. Where can we say that we have 2D or 3D printing in terms of the thickness? Let's say we're thinking on PVD technology, we have very thin layers. You show also nanometer scale thick layers. Do you have any comment on this?
Yeah, I think that's a good question, right? So what's the differentiation between the 2D and the 3D and printing in here? If you think about the devices, of course, they're kind of very low in terms of the Z dimension, right? So they all spread it on surfaces. But nevertheless, you think about it, you need to have insulator layer. Then it's normally in our device architectures, we come to any of the device, we'll come to semiconducting channel, then we will need to have insulator and the gates. So we are building them in a Z dimension. Now, does it qualify to call it a 3D? I think it's a question of community preferences. If you're coming from a structural community, they will probably say, no, it's not really the 3D, it's all fairly flat. But in the same time, if in a functional community, that the Z dimension is very important because this is the single layer. If it's sensor that is likely to stay in this type of form, if it's something more complex, even like a photovoltaic, you probably will do multiple layers in here to capture different wavelengths. So now the Z dimension become important and it leads to the 3D. And definitely with the devices too, the packaging. So which I haven't talked about it here, but after the device is made, you also need to package it and connect it to the power and etc. And this will come to encapsulation of the devices, sometimes in polymers and sometimes in some other materials which can maybe with a wide band gap if you capture the light and you want to transmit it all in here. So that is becoming a combination of this PVD with the laser annealing, with things like jet binding or with the inkjet type of which is built substantial height on the surface. And so the area became gray between 2D and 3D in this case. What also is interesting to again, the future direction, especially for the devices incorporation into the functional, like stretchable materials, clothing or something kind of wearable. This idea, okay, can we, even the substrate, it will be produced by the standard polymer way, the 3D way, but then on the top of that, on a different location, you print this 2D device. And then you cover it or don't cover it, depending where this needs to be. So this is all interesting possibilities in here. I think that's why people are excited about that particular, the 2D class of material, because the flexibility and the ability to integrate with the flexible substrates.
Excellent, thank you. We agree on the 2D printing as well. We have now a couple of questions here. One person is asking, what is the amount of COVID-19 cells that can be detected with the developed sensor? I think it's more, you show a little bit on the resolution.
Yeah, and I'm trying to answer, but they're looking at like here in the chart, they're showing that in their work that they have a parts per billions in terms of detection. So, that's meaning a very small amount. Now this is how they quantify parts per billions, I think, in an amount, the concentrations. So once billions of the concentrations can be detected. How small it is, I will probably leave it to the people working with virology decide, but talking to the Melanie Muratori, she's a biologist, that sensors is more sensitive than the one which is currently being used for like when you swap technique and you're putting in here. So it's very high sensitivity. That's
excellent. I have a follow-up question on this. I was thinking on the selectivity, some kind of, let's say, if we have influenza or other coronavirus, how does it work in this case? Do you know?
Excellent question. Yes, it's all about the sensor only work if you can have attaching a certain the virus, and this is where the ideas are coming. That to using the synthetic antigens, which is mimic antibodies, which basically only attach the COVID-19 to that particular location, which is penetrating through the membrane to them here. So, and this is where the biology scientists are working on that. Okay, what type of the synthetic proteins groups in here, in that case, the enzyme they find out, which can be at that location specifically functionalized only to react with the COVID-19 sensor. The other part of group is the sulfur linking that's connect to the molysulfide. And then that like, it needs, so this needs to be very specific in here in the group. And in this case, they were able to identify that thing in here. And also needs to be very short and be well attached in here. So it's quite a bit in here in biology science research in identifying the right sequence. But there was a lot of this work was done in this area. I'm not an expert on that location, but talking to my colleagues who work on that, you can tune the sensitivity to different molecules group. That COVID-19 is only one of them. You can detect, for example, things as molecular groups relevant to your level of the tiredness. So when people are tired, they have extracting certain molecular groups and it can be detected. So that's what's work going in Air Force Research Lab looking on ability of detecting how tired the personnel and things like this. So there's of course, there is a progress in that direction and more can be done. And this is kind of called for this multidisciplinary approach. So you can have, in this case, the thin film expert, Chris Muratori, and the biology sciences, Melanie Muratori, who happened to get home locked out for a couple of months and they came out with this idea. So
very nice result. Excellent.
Yeah, that's.
Well, let's continue. And we have a question here related to the second part of your talk. This is according to your experience, what are the main challenges presented by the development of real-time sensors?
Okay, for additive manufacturing, I think I was working, and that's thanks for the question. I was working with the PVD processing for many years, and I was using in situ diagnostic of physical vapor deposition processes such as sputtering to a large degree of the success. And when I started translating these approaches to in situ spectroscopy of additive manufacturing process, the challenge which I came across is on that small scales when you're collecting the signal, the process is not very stable. That's what I'm meaning, that very highly dynamic. You think about it, that when we're doing the sputtering, we're removing the target atom by atom, and then for a fairly small perturbation. And the mass is removed and the intensity is fairly stable. When we're doing the additive manufacturing, and we bring in the laser and we have a powder and not the solid materials, but the powder. And powder varies in their sizes, right? So there's also some gaps between the powder. There's also some local density variation where the gap is. And we bring the high energy beam on that of the energy of laser. then we are absorbing that energy, and this absorption will depend what locally in that particular location, what the powder sizes, gaps, etc. And as we're scanning, that is variations start occurring. And immediately we can see a big variation in the spectroscopic signal generated. Even with the visual eye, when you look at additive manufacturing through the protective glass, you can see all the sparks and all the other things that are flying out. You can see how the dynamic is. So that's this meaning now signal is going in amplitude very largely up and down. And this is the challenge. And then during this time, as a melted material evaporizing and you have metal vaporing on the front of the pool, and now we start seeing this excitation peaks appearing. So we are searching for these peaks across all this variable signal. And so our challenge is that this variation. And the way how you think to approach to that is to capture a lot of the data, meaning thousands of the data points. And then we're exploring right now the way of using machine learning tools to process this data and extract this information out of the very highly noisy fluctuating data. So we can have it much narrower our scattering on the prediction what the chemical pool composition is. So now there's maybe some way to do it on the hardware part of the tool in terms of the background correction, in terms of the timing, especially if you're using the pulsed lasers and not continuous lasers or quasi-continuous. Maybe some using the pulsed waves can give us that one. So those are challenges. Now, this is for elemental composition variation. Of course, additive manufacturing community is very big in other in situ diagnostic methods, and like melt pool monitoring, infrared for the temperature monitoring. This is all ongoing. Ultrasonics for the defect detection and the formation, the monitoring. A lot of progress is going on. We're focusing here on elemental composition component, but it's also needed understanding of the temperature gradient for the texture development. We also need to understand the defects presence and the diagnostics so we can certify the parts, and from multiple aspects, not just chemical composition, but structural, microstructural, defects presence, the porosity, etc. So quite a bit. So it is open field, very rapidly advancing because of a lot of the interest. We're glad to contribute here. And in UNT, we are looking into the spectroscopy for elemental composition, which I showed. We also have an effort in ultrasonic, working on defects and the formations monitoring, and maybe to a less degree on infrared right now, the detection, because try to focus on some of those defects and elemental composition at the moment.
Okay, excellent. Let's keep on this topic. I have a question related to the in situ, some kind of in situ Raman spectroscopy you use for MOS2 monitoring of the growth of the layers. Do you have any special requirements for this kind of Raman beams? Are they common Raman beams, or how do you install this into the PVD chambers and so on?
You're right. Yes. Let me see if I can. I promise you, if I can get a movie out, and let me just give me 30 seconds if I can allocate that movie and maybe help to answer some of the questions. My apology that it didn't somehow I didn't want to run it right away. I'm gonna see if I can be able to have it. No, I tried and I couldn't make it work. So I'm coming back. I'm apology for that. Somehow it doesn't want to, on a Zoom, it doesn't want to go through that. So, so going back to this charts in here, so in terms of requirements, so in essentially the laser incoming in here, and we only need to bring the fiber optic down and then the contact of about 1 millimeter close to the substrate surface. So as soon as it is organized, that's the only requirement is. Since everything is room temperature, there is no much temperature loading on us. So we actually use a regular objective, but we put it on a retractable shaft in here. So in vacuum chambers in here on the top, the fiber optics coming here, and then that lens assembly was moving in and out. So after the sputtering few seconds, we brought in a lens close and analyze it and then retract it out. So it's a mechanical way of bringing a lens close and retract out. Maybe there's some other ways of doing it, moving the substrate under the laser, take the signal and move it out. So this is only requirement because you have to focus with the Raman and you need to be close to 1 millimeter to the surface to be able to focus to that and return the signal. So that's, and this seems to be what's working fairly nicely in that case. No, again, apology for the movies. It doesn't seem to be working with it.
Okay, thank you.
You can get an idea. So hopefully I answer the question here.
Yes, thank you. Now you have another question. Let's say I don't know if it's related to this spectroscopy. How is the spectroscopy proof aligned to to ensure a correct reading? I don't know if it is the case or the additive manufacturing sensor.
So how does spectroscopy probe aligned to ensure a correct reading? Okay, so let me go back to that. Yeah, that's a good in here. So if we are looking at here, and that's in this case, we need to have collect the signal all the time from a melt-pool. So if we are scanning, that, we need to collect also. Essentially, we have to scan the probe together with the main laser. So the way how we did it in here, in the lens system, the stage is moving on X and Y, and Z dimension, that's the laser head, is retracting up. As you build the part in the Z dimension, that head of a laser, which also had the nozzles, are retracting in vertical direction to the top. So for us then was attaching our light collecting assembly to the laser head. So what you see then here on this, that assembly, it is attached on the bracket to the laser head. So when the laser head is retracting higher as you build in the Z, that the entire thing just move higher. So then, meaning that you're always focusing in where the melt pool is. And X and Y is a scanning of the table. And this way you're able to keep it all the time, focus it and calibrate it in terms of just from a melt pool direction. So that's in that particular case. Okay.
There's a question also related to this. Do you use high-speed cameras or any
excellent point. Right. So at that moment, we did not use the high-speed cameras, that flame spectrometry, not high speed. It's 80 milliseconds, 50 milliseconds is not very high speed. But we are right now investing into that nanosecond type of the cameras, because we, good line of thoughts for the person who asking the question. One of the way to reduce variability is to reduce the time of the snapshot and then hopefully avoid certain overlaps of the peaks or some other effects. So, and then having the high speed and a high sensitivity camera, much better than ones which we're using with ocean optics, will maybe answer the question. Of course, there's a price of cost. The ocean optic flame with a low sensitivity, not high speed camera is very reasonable price. So as you go more with the high sensitivity cameras, then the price also go up. So then became a question at what point it's cost too high for the manufacturing control. But for the scientific exploration, that's what we are now on right now. We are advancing into that direction for investing in this type of cameras.
Yes, excellent. Yeah, and I have another question here from the seminars attendees. What is the effect of influence in the molybdenum disulfide surface on the acer protein? What is the predominant interaction force in this system?
Yeah, I wish I can answer that and more, because my apology that, and I will probably refer to the papers in here which is discussing about the attachment, but we are using the sulfur linkage. The sulfur is reacting with this enzymes in here through the sulfur bridging in here, and once it's established, that just allows it for the charge transfer and injection into the molybdenum disulfide, which is then we're using is essentially as a resistor. So once you have additional charges there, you can have it detection. But in terms of what's the contraction of the end of that molecular enzyme group and a particular reaction with the sulfur, I would probably refer to those papers in here, because again, I'm not an expert. I'm using my long-time collaborators, Chris Moratori's work in here to highlight the use of this 2D manufacturing materials in here.
Yes, I was expecting more questions on the COVID topic, because we are working, well, I'm not working, but I know some of the colleagues are working on COVID-19 sensors. So this is a very interesting work they should address with Christopher. I hope they can.
Yeah, and I think that Christopher was visiting CIDESI a few years ago.
Yes.
So, right, so we worked together for many years. Of course, we will talk tribology, because molybdenum disulfide is a very low friction materials. We worked for years with that. And now we are looking into that using as a sensor and through the work. Sorry, Guillermo, you're on mute, so I don't hear the question.
Yes, thank you. Are there the laser annealing conditions you use for your kind of writing? Are you doing this inside the PVD chamber? And
yeah, ideally, if we can do it within the PVD chamber. At that moment, we don't have that. So what we grow is we grow them, molybdenum disulfide, tungsten disulfide, boron nitride, we all grow them in PVD chambers. The annealing is then outside. But what we are actually doing right now, that we to protect molybdenum disulfide and tungsten disulfide from the surface, we're growing molybdenum disulfide structure, and then we grow boron nitride amorphous right on the top of it. In PVD, just one step after another, just two different targets. And then after extracting from the chamber, we'll anneal it through boron nitride. That's an interesting part of that, is that boron nitride is a white band gap material, which is meaning it is very transferred to laser beam coming, which is absorbing by molybdenum disulfide and by the PDMS. So, and this allows us to protect the surface from the oxidation. So we're doing these experiments now. Hopefully we can share some results, but this is the sum of the first results was done years back, when you can anneal it through the boron nitride on MOS2, and you're annealing it, that red curve, and you can see it's that molybdenum disulfide peaks coming up and the boron nitride. So that's it seems to be one of the way of doing that. Now, maybe in the future we can bring annealing right into vacuum chamber, but then we need to think about how to have a laser window and bring it the beam in.
It's
So
how-
that's more hardware type of the things. Right,
yeah,
question.
sure. Which power conditions do you use for these treatments?
Well, what we're using that using the 248 nanometers lasers. We also used flash lamps, arc flash lamps of different techniques, different wavelengths. Sorry, and those we found out that interestingly, not high dependence on the wavelength, high dependence on the dose, on the joule per centimeter squares, but not on the wavelength. And we a little bit perplexed by that because we thought the absorption will be really depending on the wavelength. And one thing which we're thinking is that the PDMS is highly absorbing, so we are absorbing directly into the PDMS, and MOS2 is right on the top of it and get annealing. So it is still hypothesis, which is our students are working, and hopefully we can have the scientific answers to.
All right.
Right now we have more like technological observations, and we try to understand how that's exactly, where the energy is deposited to the interface, and also to PDMS, how that heat get translated to the enhancing the crystallinity. This is still so far questions which we're trying to answer.
Mm-hmm. Yes. Okay. Interesting. And the second part of your talk, you showed that iron nickel 3D printed structures. Are you foreseeing any applications for these alloy systems, or just?
Yeah, right. So the question is why you choose the iron nickel? Well, we kind of was thinking about it we want to have clear elemental composition, because we did try that on titanium Ti6-4 alloys. We tried also on some TNZP alloys. But when we have multiple elements, it's very hard to differentiate. You know, we want to have something more simple. And iron nickel, it came to us because we thought, okay, maybe it's of the interest to some, in terms of elements, the nickel can be found in multiple parts, and iron as well too. And we able also to work with this elemental powders. Iron is elemental powder, more or less stable. Nickel is also, so we can have elemental powders and mixing them up in different proportions. So, and that was our line of thoughts. So it's less driven by the intended application, and that's why it is iron and nickel, and more having the model system which we can work with fairly easily without having elemental powders working through that. So that's the selection. And when we're running, for example, Ti6-4, we see titanium, we see vanadium, we see aluminum. Now we have the 3 peaks to track. And but we also wanted to change one powder to another powder composition. So that we found iron and nickel just one of the suitable to do that.
All right. Thank you for your answers. I don't see any more questions from the audience. Any more questions, guys? You have the chance to ask one of the world leaders in this kind of topics, but I don't see any more questions. So I want to say thank you for your very nice, interesting talk, your answers, and I think we should collaborate in these topics. We're also working hard on all these topics you mentioned, and I see a very bright future for these things.
Yeah, well, you have extended, you have invitation from me to visit us, and whenever this opportunity will come, we'll be glad to show all our additive manufacturing center, which we built in situ, what we're advancing, and we're looking for this collaborative maybe opportunities for us to
Excellent.
work.
Thank you. You get a virtual applause. Thank you again.
Thank you, Guillermo.
Keep safe.
Thank you everyone who invited, and that look forward to connect in person. Look forward to the conference. Thank you.
All right.
Andre, thank you so much for everything.
All right, thank you.
See you soon. Vamos a pasar a una breve pausa. El descanso es hasta las 11:30 y los esperamos a las 11:30 para la conferencia con el Dr. Jan Haubrich. Él nos va a platicar sobre aleaciones de titanio. Quédense conectados. Ujú. Hola a todos, muchas gracias por la espera. A continuación voy a hacer la presentación de nuestro invitado de esta conferencia. Jan, thank you so much for being here. So, well, Jan Haubrich is a materialist scientist with a background in physical chemistry. He's working at the Institute of Material Research of the German Aerospace Centers as leader of a research group. In recent years, he concentrates mainly on metal additive manufacturing, as well as joining and bonding technique. His experience is particularly on laser powder bed fusion of titanium, nickel, and copper-based alloys. The group uses laser powder bed fusion for components such as LH2 turbopump impellers, turbine blades, or small-scale combustion chambers, with novel cooling designs that are being tested at the German Aerospace Center's turbine or rocket engineering testing facilities. Thank you so much, Dr. Jan, for being part of this seminar. Please take the word.
Thank you very much for the invitation. I'm very proud to be allowed to talk here. I hope I can give you a nice overview over the activities in 3D printing and additive manufacturing of metals that we are working here at the DLR in Cologne in Germany. Please let me know whether you can see my screen now.
Yes, doctor, we can see it perfectly.
Thank you very much. So I will give you about a 45-minute presentation. I'm very open to asking questions in between or after, just as you like. Please do not hesitate to ask questions. So I'm using the example of a shrouded impeller that we manufactured in one of our projects from titanium 6-4 with laser bed fusion, here to highlight a few research aspects we are having in the field of additive manufacturing. And thank you again, the organizers for the conference, for inviting me to this event. I hope this is going to be interesting for you. So here at the DLR, we are doing additive manufacturing for almost 10 years now. Since roughly 2012, 11-12, we started the activity. We're working on two, let's say, main topics. First is the material development and process development for existing materials. There we have the conventional alloys like titanium 6-4 or the titanium aluminides, TNMB1. We're recently working a lot with copper alloys for rocket engine applications. We are having some projects and topics with nickel-based materials for high temperature, high strength applications, turbine engines, for instance. And we are also working on structural parts for satellites using aluminum alloys. Besides those standard alloys that we call them usually conventional alloys because they are readily available and generally not have been developed for additive manufacturing, we also work on tailoring existing alloys and developing new alloys specifically for additive manufacturing. For instance, we're working on titanium alloys. I don't know whether you can see my cursor, perhaps. Can you see my cursor?
Yeah. Yes, doctor, we can see
it. Yes,
perfect, perfect. So we're working, for instance, on the titanium alloy side on new alloys that do not suffer from this anisotropy and texture formation that you have in a process with a directional cooling. Or we're working on materials that benefit strongly from the very high cooling rates laser additive manufacturing provides. For instance, we have ultrafine titanium ion eutactics we're working on that form only with very, very high cooling rates, but they exhibit very high strengths at high temperatures. So interesting material that needs to be fursed. The other part of the work, or the other main column of our work, is component manufacturing at the DLR. DLR has like 9,000 people at the moment, with many institutes working on design and testing of components, for instance, for rocket engines. And in those projects, we mostly cover the manufacturing sides of components. The other institutes design and later on want to test and to further. And in those projects, we generally start from powder characterization, then developing manufacturing parameters over component building, up to manufacturing the demonstrators for the other institutes so that they can, for instance, do the testing. And one of those examples I'm going to show today. Here is a small selection of components we've been working on in the past, and in the aerospace sector and aeronautic sector, it's oftentimes compressor wheels shown on the left. Then we have the shrouded turbopump impellers that are important for turbopumps in rocket engines, injectors for rocket engines, structural parts, or more recently, we're working a lot with copper, chromium, zirconium alloys. On the right-hand side is a first demonstrator of a new combustion chamber. We were just working on a new project, and that's quite challenging. So the technique we are using at the DLR is laser powder bed fusion, or often also called selective laser melting, SLM or LPBF then, in which we have basically a fixed base plate that is going to be filled with CAD models to be printed. Then they are going to be processed in a layer-wise fashion. You see it in the center. The laser works on one surface then. It's generative, meaning it's layer by layer. It's like Lego for the children, essentially. And what you get in the process then in the end is your parts hidden in a powder bed shown on the right-hand side. They are basically covered around with the powder. And if you remove the powder, then you can get the final build from the machine. And that those parts that you generally build have to go to post-processing. Here at the DLR, we're using a customized SLM Solutions 280 machine. So it's a machine that's roughly 8 years old now. It has two specialities. One, a high temperature build place platform that we can use for very small amount of powders and for very high build temperatures. What I'm going to show today, however, is built with the standard build plate with the large one shown here on the top. The big build plate only reaches 200 degrees Celsius, and that's enough for titanium generally. Another specialty in our machine is an in situ melt pool monitoring device that allows to monitor in situ the thermal emissions from the laser process. And I'm going to show you what that's useful for in the end of this talk. So today I've chosen the example of a shrouded impeller that we've done in this project called Selective Laser Melting of Rocket Engine Components. And that consisted of 3 aspects: the design of a rocket turbopump impeller, the development of the manufacturing chain or AM process chain, which in the end resulted in a successful spin test. The rocket turbopump impeller itself, the component itself, is not an SLM design, as most of you will probably readily recognize. There's lots of flat internal surfaces that make manufacturing quite difficult. It's a conventional design that has been developed for a 2-part manufacturing route with a base part and a top plate that are going to be or have been in the past braced together. And our goal in the project was to see whether we can modify that slightly, but only slightly, in order not to sacrifice performance, and manufacture this part from one, or this component in one part. It's a highly loaded part in terms of rotations, 55,000 rotations per minute. So we went for the high strength titanium 6.4 in this case for the material side. So first thing that we at the Institute of Material Science had to do with this component was to develop the AM manufacturing route, and that started with process parameters, so laser parameters essentially for the SLM machine. Other aspects included residual stresses and characterization of the mechanical properties of the materials that we generated. For the turbopump impeller, the surface quality is an issue because of the aerodynamic properties. For the fuel transport, it's liquid hydrogen or liquid methane that's transported by the impeller. Other aspects is process stability, reproducibility, and quality that we had to work on in order to ensure the components would satisfy quality needs. One big part of the work we had to do here is the development of a build strategy, including supports and part orientation for this component, and including the post-processing steps that affect, again, all the other steps. And in the very end of this talk today, I would like to show you a little bit how the things that we developed in the beginning of our project on coupons, on small cubes or so, in terms of process parameters or mechanical properties, actually will relate to the mechanical properties or the properties of the material in the manufactured component in the end, because there's going to be a slight surprise there. Some topics I grayed out here, which means I will not be able to talk about that today in the brief time, but if you have questions regarding that, I may be able to answer them. So first part of my talk will be the development of process parameters for manufacturing titanium 6-4 on our machine. And here we started with porosity, then continued with investigations of microstructures and development of heat treatments for the as-built material that we get out of the machine. This is going to be something that you very well know already. That's been published in the literature for more than 10 years. Many studies of this kind on a variety of material, from aluminum alloys to steel and other materials, typical porosity studies, where you generally find that if you have too low process energies, so below the optimal energy, E-opt, then you get the typical balling effects, meaning you have too little energy, the material doesn't melt entirely, and you get these kind of unmolten particles in the material that leave these very sharp, edgy cracks. And you see at the bottom of these round shapes here, you still can guess it's powder particles that are not sufficiently molten into the material. That's on the low energy side. If you have too much energy in the material, on the right-hand side here in red, you get this typical keyhole mechanism, keyhole pores that is known from welding already, that also generates porosity in the material that you like to avoid. And in the middle, you will have an energy window where you have very low absolute porosity, but at some points, and you can guess it here at the top here, sometimes there are some residual cracks in the material, but they are often those cracks here on the left-hand side, balling type cracks, very sharp cracks that you actually would like to avoid. So maybe you want to go to the right-hand side of the processing window where you at least have round pores that don't generate very high stress concentrations in the material. What you find a lot in the literature, and what we also found, is if you then draw diagrams that at the bottom have an axis that shows the process parameters, either laser power or velocity, scan velocity, or a convoluted parameter like the energy density, you get these kind of trends where you have an optimum in the middle, and at too low energies or too high energy densities, the porosity starts to kick in, either binding faults or balling, or on the other hand, the keyhole pores. And so you have generally a process window in the middle that you accept in terms of porosity. It's like below 0.1% or 0.05% is acceptable for the process in our case. And now with a material that's optimized in terms of porosity, we started wondering at the microstructure that we generate with the process here. And then we picked an energy at the left-hand side of our process window, 77. That's a value that you will recognize in the further slides a number of times. And we picked a processing parameter set with a volume energy density of 145 here. That corresponds to the right-hand side of our porosity optimized parameter window. It's a little bit higher porosity here, but let's say these border our parameter window. So we asked the question what the microstructure looks like and how we have to adapt the microstructure in order to get proper mechanical properties. These images show some SEM data, SEM images of the as-built microstructures that we get from the process run at 200-degree base plate temperatures. On the left-hand side for titanium 6-4, the very typical martensitic structure that you get due to the very high cooling rates of the process. The SEM shows a lot of lattice defects here, especially twinning in the material, dislocations that I will come back later. This is very typical for SLM titanium materials at low volume energy densities. On the right-hand side, you see the parameter set corresponding to the right-hand side of the parameter window, which looks already a bit different. You see these high or brighter borders here in between this martensite Las and alpha prime grains. So going to higher process windows already gives you a different microstructure. And in fact, XRD shows that there is already 2% of beta phase formed in this material. It's a BCC phase, whereas the martensite, the alpha prime, or the alpha phase in the titanium system is an HCP phase. So increasing the volume energy density increases the amount of beta phase. It starts to decompose the martensite and stabilize the microstructure, which I come back with the heat treatments in a moment. So first thing we asked in this case, for instance, can this effect be enhanced further if we further increase the volume energy density or the laser energy amount that we put into the material by changing the scan strategy. For instance, on the right-hand side, you see the thermal profile here that we have by lasering a simple cubic specimen with 2 layers. You see this main spike at the beginning, and the second layer follows, and there's a buildup of the basic temperature of the specimen. Now, if we reduce the hedge distance, so we basically scan the same surface area of the cube much slower, much tighter in terms of pattern, and then we need basically double amount of time per specimen, then we get an increase in the space temperature, meaning we put more energy into the same specimen, and this indeed did stabilize the microstructure further. That's an effect that we call intrinsic heat treatment because it's unavoidable with the laser processing itself. It's the laser energy itself due to the changed scan pattern that increases. So that's where we termed this, or formed this term intrinsic heat treatment here. And you see now very clear, bright lines. A lot of beta phase has formed here. The microstructure looks very different compared to the martensitic microstructure on the left-hand side. So next thing we did is, of course, for the titanium systems, we need a few heat treatments. We need a stress relief heat treatment in the beginning in order to avoid part distortion, for instance. It's generally done at subtransient temperatures of around 500 to 650 degrees Celsius. And we investigated further heat treatments in order to obtain very stabilized alpha-beta microstructures here, without sacrificing this very fine grain structure that you generally get in the SLM materials. Shown here are HE-XRD spectra, so XRD spectra taken at the synchrotron in Hamburg at DESI. And what you see here in the bottom is the 145 joule per cubic millimeter as build state, where you see a very small signal for the beta phase, roughly 2%, and then going to higher heat treatment temperatures, 400, 530, 650, and 800 degrees Celsius for 2 hours each as an ex situ heat treatment in an oven of the material. You see that this beta signal here changes, disappears a bit at 400, and then at higher temperatures, we get a beta 200 signal, and we also get other beta signals growing in the spectrum that are very clearly discernible. So one thing that we directly see, the beta phase changes due to the heat treatments. It does change in terms of chemical composition, and it does change a little bit in terms of orientation. And on the right-hand side, you see some SEM images corresponding to samples treated in that way. At the bottom, you see this, it's difficult to discern, but there are these fine white films in between the martensite lath. And going to higher temperatures, the films get more pronounced at 400 degrees, but they completely break up at 530. Here we only get very fine white particles in the SEM images of the materials. And these particles coarsen at higher temperatures, which you can see here in the yellow and red framed images. So there's a lot happening in the material. And this we already get from SEM and XRD from diffraction, and wanted to understand the process further in order to optimize the microstructure. What we get from the XRD further is if we calculate the lattice constant of the beta phase, A beta as a function of the heat treatment temperature, then we get this kind of diagram where you very clearly see, okay, here is a discontinuous change in the beta phase lattice parameter. There is a minimum at about 530 where we have these fine particles. At 400 and in the as-built state, we had these fine, thin white films between the martensite lath. And here we have this coarsening particle type microstructure. So there's this kind of resembles itself in the lattice parameter. And that's already telling us something about the composition of the beta phase here. This lattice constant typically goes down if the amount of beta stabilizers, so vanadium and iron in this alloy, increase in the beta phase. This kind of shrinks the lattice constant. So this is already a strong hint that there is a partitioning effect and diffusion going on in the material. In order to further understand that, we had a cooperation with the colleagues of the Max Planck Institute in Düsseldorf nearby who did atom probe tomography. So it's a tomography used chemically using a mass spectrometer essentially for detection of single atoms with very, very small samples, but very high sensitivity. And this, for instance, allows us on the right-hand side to characterize the shapes of the beta phase more. Shown here is an isosurface of vanadium, basically a surface that envelops the regions that are particularly enriched in vanadium. And shown here on the left-hand side is the as-built state, where you can kind of see at certain rotation angles film-like structures and a little bit plate-like structures at the bottom that I will show later on again. Whereas here on the right-hand side, at 530, this film-like structure is mostly broken up and it looks more like particles. So the APT is going to give us a lot of insights in terms of the morphology of the beta phase, but also the chemical composition. And in fact, now on the left-hand side in the diagram, you see the composition of the beta phase in terms of vanadium that we get from the APT. And it confirms that in the as-built state, the beta phase is less enriched in vanadium than at 530. And this enrichment reduces again when going to higher temperatures. Yeah, the APT is a very powerful technique and allowed us further insights in the formation of the beta phase during our treatments and the SLN. Here is shown the distribution of the iron in one of those samples. Iron is another beta stabilizer. It's very sensitive in terms of the location of the beta phase. And you see on the left-hand side these elongated structures that correspond to the typical films. It's the exact same sample that I've shown with the vanadium a second before. So this is the film-like beta phase in the as-built state, but it also shows very fine elongated precursors growing from that, for instance here, or a larger particle down here at the bottom. And this allowed us to understand that the beta phase formations due to the heat treatments or due to intrinsic heat treatments, so due to energy input essentially, leads to formation of new beta phase along lattice defects, like dislocations, which we could confirm here with APT in our work. APT further showed us or gave us information then on the beta phase in the different conditions. Here you see on the right-hand side in the bottom axis, the different kind of beta phases on the as-built state and the 400 up to 650 degree heat treated states. And you, without going into details, you readily see in pink, there's the amount of vanadium that changes dramatically. It goes to a maximum at roughly 530 degrees Celsius. Now this is mass percent, I should note, whereas in the previous HEXRD, it's volume percent from the READFAB analysis. But again, nonetheless, APT confirms the same trend. There's a maximum of diffusion of beta stabilizers into the beta phase at about 530 degree, and at higher temperatures, this trend changes again. And this way, we were able to learn a bit about the beta phase formation using the combination of techniques. And we were surprised to find that the partitioning is actually most pronounced not for the main beta stabilizer vanadium, but it's most pronounced for the iron in this case, much more sensitive than the vanadium, which also allows to better track all these precursors in the material, for instance. So in summary, we find that the heat treatments lead to a diffusion-driven martensite decomposition and the stabilization of the microstructure, so that at higher heat treatment temperatures, we end up with stabilized alpha-beta microstructures. So one maybe rather interesting detail is the grading effect that you generally get in SLN or LBPF, which is due to the directional cooling, because you have a directional physical process. You put in the laser energy from the top, you lower the build place down towards the bottom with each layer, and the material is also towards the bottom, massive material, so the heat flux is going to be downwards towards the base plate. So it's directional cooling, and this kind of symmetry that you enforce on the physical process can lead, or should lead actually, to responses in the material. And in fact, if you look at the microstructure along the height of a simple cubic specimen, you will find this kind of effect. Shown here is this very high energy parameter that I've showed in the beginning, where we have this very strongly stabilized alpha-beta microstructure in the as-built case. And you see in the SEM images taken from the bottom and the center of the sample, that is this kind of very nicely stabilized alpha-beta microstructure with a lot of beta phase. Whereas if you take a an SEM image from the top of the specimen, it's still this very metancitic microstructure. And that's simply due to the fact that the bottom layers have seen more laser passes of top layers that have been added to the specimen, whereas the top layers only have seen a few, so only a few times laser energy input in the material. So this is something you have to always keep in mind in the material with SLM or LPBF. The material that later on will be generated in a component doesn't have to be homogeneous. And AGXRD here shows a little bit this trend. On the left-hand side, the axis shows the height of the cubic specimen, 10 millimeters. And the blue curve shows the volume fraction, again, of the beta phase in this case. And in the stabilized region, which extends to roughly 8 or 9 millimeters here, 8.5 millimeters, you have roughly 6 to 7% of beta phase in this cubic specimen. Whereas at the top of the specimen, you switch to a martensitic microstructure with very little beta phase here at near 10 millimeter height. So that's something to keep in mind. Exactly. We've done a little bit of tomography on these materials to try to find out whether these are simply platelet type of beta films or interconnected 3D networks. And we've done that with phototomography and Grenoble at the synchrotron. So a tomography that has a resolution of roughly 10 nanometers, very fine resolutions. And what we found is that we actually don't only have single platelets from the beta phase here, but these platelets are three-dimensionally connected or interwoven. So it's a 3D structure. And this beta phase, actually, I should have mentioned it in the beginning, is very important for us because it's the phase that will allow the best ductility, or it will be the phase that will be easiest deformed in the material. The alpha or alpha prime are rather high modulus phases that are not accountable for the ductility in the material in the end. So another issue that, or an issue that I want to talk about today is the post-processing of the SLM components or specimens, because in my opinion, or probably not only my opinion, but opinion of many industrial users at the moment, surface processing is one of the very key issues. Without resolving this issue, all the additional freedom that you have with 3D printing is not worth too much. Surface quality is very important in terms of the mechanical performance or aerodynamic performance of components. Because if you have crack-like and poor surface, very rough surfaces with notch type of defects due to the process, you have a very poor fatigue performance. That's something you like to avoid. Roughness in the SLM process, however, is something that's intrinsically present because you have this generative step-like process. You see it on the right-hand side. It's like layer by layer process. So this will have an effect that you cannot entirely avoid. It belongs to the SLM process or LPBF process. If you have vertical planes, you can even have inward melting and down melting at the sides of your specimens, which can lead to this kind of notch effects or over melting. You see it here at the SEM image at the bottom, that you can discern certain layer structures from subsequent layers, and this can leave kind of undercuts. It's a very rough surface, poor surface quality actually. And if you go to downskin surfaces, so surfaces that end up over the powder bed, this inward melting of the material at the edge is actually very pronounced with copper alloys, for instance. This is very critical, something that is a limiting factor for 3D printing today. So we must find processing strategies as well as post-processing strategies to address these deficiencies. With SLM, we have the advantage that we have a lot of parameters that we have control over. That's particularly the laser parameters and the scan strategy. We've, in the beginning of my talk, talked a lot about the volume parameter optimization in terms of porosity and microstructure. And the volume is basically shown here by the green arrows. That's the volume hatching of the specimen. In the shaded green color, you see the width of a typical melt track in titanium 6.4, which is roughly 200 microns. So the single hatching lines of the laser will overlap a bit. In the contour region or surface region, things get complicated rather readily. You have these red contour lines, which you can have different numbers of, and in between the green volume, you have a fill contour shown here in yellow that overlaps those regions. And adjusting these overlaps, the distances, the parameters in between, gives you a large parameter space with possibility to optimize your surfaces, but it's also quite tedious, let's put it that way. So we've done that on different types of specimens that have different surfaces, up skin, side skin, down skin, vertical thin walls, and things like that. And actually, there is quite some possibility to optimize parameters here. You see a trend here that by increasing the power on the contour line, you can reduce porosity, the surface roughness from roughly an arithmetic mean surface roughness of 15 to roughly 12, just by changing the laser power and the scan velocity in combination, such that the volume energy density of the laser track still stays constant. So increasing laser power means also increasing the scan velocity accordingly. Okay. So adjusting the laser parameters helps a bit, but what we found helps most is actually changing the scan strategy at the surfaces. So it's the question whether you only do bulk hatching, then it's only those green vectors, or you start putting contour lines and fill contour lines, different numbers of contour lines, 2 in this case, 5 in this case, and with different differences and also with different scan order before or after the green bulk lines. That gives you a lot of space to optimize the surface quality. This is kind of shown here. It's a little bit of complicated diagram. I apologize. At the bottom, you see the hatch distance, and on the left-hand side, the surface quality in terms of SA again, the arithmetic mean surface roughness. And I want to point out particular points. This is in blue, highlighted here, the SLM standard parameter that I've been using in the past, which gives you, depending on the sample site you have, a surface roughness at the order of 12 microns. And by optimizing the number of contour lines and the contour parameters, we were able to reduce that quite a bit. Put an arrow bar on this because sample positioning on the base plate and reproduction leads to changes here. So I wouldn't be too specific about the exact value, but there is a trend that we can improve that by changing the scan strategies that the manufacturers provide. So that's actually an important thing. Catch-22 in this case is you don't only affect the surface quality in this case, you also affect the residual stresses. And we did that with measurements at the synchrotron Bessie in Berlin for different specimens that have very different surface scan strategies and scan parameters that result in very different surface qualities. And you can roughly see that a surface that has a very high roughness here at around 30 micron will lead to very low surface surface residual stresses in this case, in build direction, stresses in build direction. Yes, very low surface residual stresses means you don't get cracking of your part. On the top, we see a little image of an injector ring, and you see here cracks in the surface. This one was manufactured with the parameters that gave us the best surface quality. So on the left-hand side with the red circle here. But the residual stresses here are so high that the injector ring cracked where on the inside channels are positioned. So it's actually poor manufacturing strategy. So we had to go for kind of an optimum or a compromise here, allowing for a little bit improvement in terms of surface roughness and not too high residual stresses. So this is, let's say, the backside of the medal in this case. We couldn't optimize it as much as we'd like have. So what we had to do in the project then for the impeller was developing or finding post-processing strategies. If you nowadays walk about over the Form Next conference or big market show in Frankfurt we have every year on 3D printing, there's more and more companies that provide services in terms of surface post-processing for parts and specimen. On the right-hand side, you see a couple examples with some light microscopy images of the specimen after machining. And you see that, for instance, plasma polishing or this micro machining process, MMP, leads to much smoother surfaces. On the left-hand side, you see a simple diagram for vibrational slide grinding on the top with a very, very simple machine that we've done here in the lab with this kind of grinding medium, a kind of ceramic material medium that we run the process in a couple of hours. See at the bottom the process time, and you see how the as-built roughness from 0 hours goes down a little bit at a cost of edge rounding. But we investigated a couple of processes. We sent specimens to external companies to get them post-processed, and in this case, we found a suitable processing strategy for our impeller. So with that, I will now come to the build strategy for the impeller itself, which is based then on the previous results. The first aspect that we have to take care of when looking at manufacturing of a component, you probably all know, is the orientation of the component and the question of supports. For this impeller, we had the option of, let's say, 2 basic orientations, one a diagonal one, something like 45, 50 or something degree with respect to the surface normal. This orientation has the advantage that you will need fewer internal supports to support basically the top surface, the downskin surfaces inside the part. But it does have the disadvantage that any anisotropy that the process, due to the directional vertical cooling basically gives you, will not be oriented along the high symmetry axis of the impeller itself. So you don't exploit the anisotropy here. It's diagonal in that sense. That's better for the horizontal orientation. So there you would have 2 main axes in the texture or anisotropy of the part. One would be the build direction, vertical, and the direction in plane or orthogonal to that would be the direction that would have different mechanical properties in the material. So this orientation would be more suitable in terms of engineering using the mechanical properties. But it is more complicated in terms of internal supports because you will have all these flat downskin surfaces of this top plate that need to be supported. Otherwise, they will not be stable on top of the powder bed. So manufacturing-wise, this is the worst choice. So we started with the diagonal orientation. We started developing support strategies. On the left-hand side, there is an example of one orientation with very massive supports. Essentially, we could have printed a massive titanium bulk below this impeller that wouldn't have been much different. On the right-hand side, one of the early tries with a minimal amount of supports, slightly different orientation of the impeller, but you see it's a lot less. And even with these 2 support strategies, even with this very massive amount of supports on the left-hand side, in the images after processing, you see this front support is bent off. It's ripped off from the base plate. So there's very high internal stresses, and this wasn't successful either. If the supports detach from the base plate, that immediately means you will have distortion in the part due to thermal residual stresses. On the right-hand side, from this perspective, it looks a little better, but you'll see detailed images here. Also there we had serious troubles. So in both cases here, it's on the left-hand side, it's detachment at the base plate with the supports. On the right-hand side, it's also detachment of the supports, but this time between the supports and the part itself. And on top of that, we found with this orientation for the right impeller that we have serious issues with surface quality and precision of the geometry in this top area where we have downskin surfaces melting over the powder bed. There's this very strong inward melting here. And in order to address all these issues, we went to an, let's say, empirical development, iterative development of build strategies with customization of supports and analysis of the part in between, which then led to the build strategy shown on the right-hand side, the 10th impeller, which has a rather complicated support strategy. Some aspects that we addressed here were this high surface roughness in this top surface. We had different kind of internal supports that we used here. In the end, we ended up with these 3 supports shown in the 3rd picture. These 3 supports are rather easily removed and they don't leave traces on the part itself, which is very nice. That worked nicely. And for the other detachment issues due to the high thermal residual stresses, we developed custom support strategies. Here you see some images that show how drastic these thermal stresses can be. Very high stresses, millimeter deformation of the parts, cracking in the supports and things like that occur here. You see some deformation here on the right-hand side. This part is all but round. So we had to work on the supports here. And in the end, we were successful with a support strategy that contained 14 kinds of different customized supports, but it worked. So this is very empirical, I must say, at this point. This was like 3 years ago now. I would today wish for more support from process simulation here, because a lot of these empirical steps, probably using the right simulation, are simply avoidable today. So now to conclude my talk, I want to give you a little bit of insight how the process parameter developments that we did in the first part of our study on the coupon level, small cubes or so, actually do relate then to the mechanical part properties that we have in the manufacturer demonstrator. And there we found actually a couple surprises. For this, we can use this tool in our machine called the melt pool monitoring that probably many of you already also know, because today it's more or less standard in LBPF machines. We were one of the first customers to use it. It's basically a pyrometric tool with 2 photodiodes. It records in 2 wavelength regions thermal emissions from the melt pool itself. It follows the optic of the laser, so that we get basically a thermal response from the melting material itself. Meaning it's at first order a tool for measuring the temperature or thermal emissions and the melt pool size, its convolution there. It gives you data in a layer by layer fashion. On the left hand, or in this image, you can see how one layer is hatched by the laser in a checkerboard fashion, and simultaneously the data is recorded by the MPM. And if you combine this kind of layer-wise data from subsequent layers into a 3D image and a 3D data set, which I hope you can see here. I think this time we will have problems with the video. Sorry for that. Last time it worked, but apparently I will restart the talk. So the trick is, with this MPM data, you can combine these layer-wise information into a full 3D data set, which we are doing with our Institute of Software and Computation here at the DLR. They developed a small software code for that, and I'll show you now how that is useful. And we did that by producing one of those impellers with this very high energy SLM parameter set that gives these nice alpha beta stabilized microstructures here. We only manufactured part of that impeller, a cut from that impeller to a certain height. And at the same time, we recorded this melt pool monitoring data shown here. And on the right-hand side, you see a cross section through this 3-dimensional data. And what you readily will recognize and immediately will recognize here in this data is the increased heat in the downskin areas. These are known to overheat. And you also recognize that there are other regions in the part that show a little bit increased intensity, and regions that have a lot less thermal radiation in the MPM during the melting time. So the question here is, what's the microstructure in this manufactured part finally looking like? And is the same microstructure with the 6 to 7 volume percent of beta phase still achieved? So it's the intrinsic heat treatment from the parameter that we got from the cube study still the same, leading to the same result here. And to understand this question, we again went for high energy X-ray diffraction in this case. On the left-hand side, you now see again the MPM cross-section of the MPM data from the pyrometric monitoring. And on the right-hand side, the beta volume fraction across this part of the impeller, where you have the amount of beta phase on the scale on the top. And what we found is that, as expected, in the regions here, in the downskin regions, where the part gets particularly hot because it's over the powder bed and the heat cannot be conducted away from the part readily, there is an increased amount of beta phase, but it's only increased to like 6% or so, whereas the bulk of the part itself has only about 2% or 3% of beta phase, which is a lot less than we found in the cube that we produced separately. And this shows very readily that you have to be very careful with coupon studies and transfer to components. The component geometry, but the processing conditions directly and indirectly influenceable processing conditions will affect the material properties in the resulting component, despite using the same parameters that are developed on small components or coupons in the beginning. And this is rather easy to explain. If you look at the data set of MPM data from a full impeller, you can see here. Oh, can you still see? Yeah, you can still. I hope you can see.
Yes.
Fine. You can see here that towards the top of the impeller, the intensity is a lot increased. So it's getting hotter when the final part of the impeller, the top part, is being manufactured. And the simple reason is the cross section per layer. Here at the bottom parts with the supports and so on, you have a lot of area that you have to laser, which takes a long time. At the top of the part, you only have very small parts that still need to be finished. So the laser will finish a layer rather quickly. The layer time is going to be short. When manufacturing this part towards the top, it's going to decrease, meaning with the next layer, the laser comes back to the same spot in much shorter time at the bottom, and then you get the increased heat input, again, an intrinsic heat treatment, which is not effective at the bottom because your layer time is so high that when the layer comes back to the same spot above the previous layer again, it's already cooled down. So with such a large part and such a large layer time, this intrinsic heat treatment parameter that we developed on the small coupons is actually no longer effective. So you have to really look for small effects like the processing time per layer. If you change, for instance, the number of parts on a base plate during a build and make one build with a single impeller and one build with 6 impellers on them, the material properties will be different between those. And this is simply a time effect in this case. So it's kind of an indirect effect that's quite, I think, quite understandable and not very surprising when you think about it in the end. But we were surprised during our studies how much influence this actually does have. So, and with this, I want to finish my talk now. In our project, we were able in the end to produce this impeller, to process this impeller with heat treatments. We used a heat treatment actually in combination with hot isostatic pressing here, because this gave the best mechanical properties. And it also ensured us that we didn't have, let's say, critical manufacturing defects in the parts that would in the end ruin the testing. And in fact, the parts have been tested by spin testing at a company. Burst tests at the 166,200 RPM were successful. By design, this part should have failed at this rotational speed, but it actually didn't. And we even had only very minimal plastic deformation after the burst test. So we were kind of surprised that we actually did succeed in this project. None of us would have thought, given all the challenges in additive manufacturing, that we would actually succeed here. And with this, I would like to wrap up my talk. There's a couple of topics that I could not touch upon, for instance, the heat treatments in combination with mechanical testing, so adjusting the properties for the components. I couldn't really talk about the residual stresses much. I couldn't talk about a number of other topics, for instance, improvements of the machine technology in terms of process gas atmosphere and so on. But I hope I could convey you that actually laser powder bed fusion and additive manufacturing is quite powerful, not only interesting for materials researchers and engineers, but quite powerful. The material in the coupons and the parts and the properties of both are linked intrinsically by the process, meaning we have very strong leverage to influence the material properties in parts and components by all these process parameters. This is good, but on the draw side, the bad side, it also means it's quite complex research that one has to do in this case because of the many influence factors that we'll have here. In the future, I hope the quality of simulations and the reliability of simulations will improve rapidly, because only then I believe the full potential of additive manufacturing can be exploited at all. Otherwise, all this research and development to get one component working after manufacturing, in the end, it's just too extensive. Yeah, and this brings us to the ugly, I would say. It's very expensive. Still, additive manufacturing reproducibility is an issue. Even comparing results from identical machine manufacturers with identical machine types set up as two different locations can lead to differences there. And another thing that I believe needs to be addressed is the development of new materials for additive manufacturing. For this titanium 6.4, it's a material that has been around long before additive manufacturing. And given that you get these very brittle martensitic as built microstructures, you end up after printing with a material that is all but suitable. And this leads to these extensive heat treatments, which are expensive. And this needs to be avoided in the future by having materials that right after printing will show you better material properties. And that's something that can only be done by materials design, alloy development. So the ugly, of course, is also a bit beautiful for us researchers then, and I hope you share this belief with me, you agree with me. It's just the more reason that we have to do research on this topic. And with this, I would like to conclude and thank my co-workers here, particularly also my head of department, which some of you may know. It's Guillermo Requena, actually a native from Argentina, who's joined our department 5 years ago and is heading the department in which my group is doing additive manufacturing. Thank you very much.
Well, thank you, Jan, for this very interesting talk. I'm really happy to see that you are doing well. This is nice to see you again, to see familiar faces again, and I'm happy to see you. Very interesting talk. This is now open for question, please. So let me check the questions. Some people said you have an excellent talk. Congratulations.
Thank you.
This talk. It was very nice. I agree on that, of course. I think some of the questions of this one you answered already, but let's say if you can add something on. In terms of metrology, how do you ensure the quality and reliability of your measurements? Specifications, tolerances, uncertainty, what kind of standards do you use? Yes, let's say.
Yes, very important topic in terms of distortion and part accuracy in the end, and something that we've so far only been able to do with collaborators that, for instance, use, this stripe-like measurement technologies that GOM or Kian's instruments use for measuring the final part geometry. That's something that we're doing that, of course, only works on the externally accessible surfaces for either touch probes or for light accessibility. For the insides, we have to rely on, for instance, computed tomography, which doesn't give you very good resolution with these big parts and poor radiation transmission through those parts, but that's what we've been doing in the past. We can improve on that. I hope in the future we will be able to start a small investment here in a small additive manufacturing lab that will allow us also to buy a small tool for geometry measurement metrology here. I hope this answers the question. Maybe I should mention one further thing. You see it here in this image here I showed here. It's a very, very flashy surface at the top. In the very end, we decided to machine the outer surfaces, particularly the bottom surface with this mount for the machine itself, for the pump itself, because this has to be very accurate, very small tolerances, and that's something additive manufacturing will never give you.
Okay, thank you. We have a lot of questions. Let's continue with this. Dr. Raimundo Arroyave is asking, what about changing the process conditions locally to escape the Pareto trade-offs that arise when considering constant process conditions through the process?
Sounds like a very enticing idea, actually. Yes, I would agree with that. In the future, I hope we will find some time to play around with this kind of, I would call them hybrid scan strategies. But I totally agree that could be a solution. Within this project, we simply were overwhelmed with all the tasks we had to do and couldn't do all of it.
Of course, yes. Yeah, he's also asking on the other. I have two places to put questions, so let me change to the other one. Jose Mercado Rojas is he said, congratulations for the awesome work, the amount of work you have. It seems that the support optimization was done experimentally. You said it experimentally, yes, empirically. What are the limitations of the current state of simulations regarding the support structures?
Yeah, there are a number of either research-based codes from universities or research institutions or companies like ANSYS or Materialize. They basically rely on thermal simulations and a very high degree of abstraction, so far as I know. There are other codes that go into, let's say, microstructure simulation with much more detailed thermal profiles simulation from this process, but they are either in their infants or they are limited to very small probe volumes. And what we really would need would be a code that can, for such a large part, without too many abstractions, really simulate the thermal profile. And from that, the thermal stresses. And one of the codes that can do that is Materialize Magics, but they basically use a very rough approach. They first ask you to print three kinds of specimen on top of your base plate that you start cutting to measure the macroscopical deformation of those specimens after cutting without stress relief heat treatment. And and these are going to be used in three directions, measured and used to calibrate the simulations. So it's a very rough approach. Qualitatively, it works. Quantitatively, I would be happy if there would be a better choice. With ANSYS, I don't have so much experience, but it's all work in progress, and they develop rapidly. So I'm quite sure in 1 to 3 years we will have something very useful.
All right. Thank you, says Mercado Rojas, for the answer. James was asking. Yes, James is asking a question also. In your opinion, what is the best synergy to complement experimental results with simulation models? Because he's doing simulation.
The best synergy?
Yes.
I can only answer that from my personal perspective. For me, the best synergy would be to use the fastest and cheapest tool for the most suitable aspect. And my background is actually theoretical chemistry. I come from calculating chemical reactions of specimen prior to synthesizing them. And I find this is a very, very suitable approach. So I would rather start with a simulation of my supports in the process before I even do the first build. That would be my ideal.
All right. I hope this answers your question, James. If not, then you have chance to answer more things. Next one. How important is to use high-speed infrared cameras for monitoring the melt pool? Excellent talk.
Mm-hmm. Yeah. There are a number of studies in the literature and in the internet where people are using these high-speed cameras. For instance, Ian Todd at Sheffield is doing a lot with that. Very interesting. I think you can also learn quite a bit from those studies. I find them very interesting in terms of the spraying of the particles around the melt pool and the stability and the dynamics in the melt pool. I think they help a lot to learn about the basic stability of the melting process for different materials.
Very good. All right. Some general questions. You mentioned the activities at the DLR. You are working on very different steps of the 3D printing processes, from starting from powders to the 3D printing process. Are you producing anywhere at the DLR powders, or are you working with
actually
products?
Yeah, we only work with partners in this case. Either we have companies that we send the ingots to for atomization. Then we can still create the compositions and have the ingots manufactured. Or we are really working with external partners that take over the complete powder side. We don't have any kind of atomization facilities here.
Okay, one more question regarding the surface finishing, surface quality. You showed us the poor roughness we can achieve with the SLAM process. The question is that it's applied, of course, to open surfaces. It could be easy to do machining just to finish the part, but are you trying to produce finished parts from begin to end only with SLM process?
That would be the ideal, that we have to avoid any kind of either mechanical machining or chemical post-processing or so on, just with the process itself. But I think simply from the theory behind it, it's not possible. Here in this impeller, I've showed the outer surfaces are machined because turning is rather cheap. That doesn't change the business case, so to speak. Much mechanical mounting surfaces that have to be highly precise have to be machined anyway, because you won't get the precision that you know and that you need. And I can give you probably a rather easy argument. You see here that there is, beside the melt effects, these melt shapes, a lot of powder particles attached to the surface. The typical SLM powder has an average diameter of, let's say, 40 or 50 microns, or let's say 40 microns, distribution between 10 and 60 or something. But let's say if you have a particle of 40 or 50 microns, your part has two sides. At each side, you have particles attached to the surface. Even if your melt tracks are going to end perfectly exactly on the geometry, which is already in this top image here not the case, then you have attached particles. Two sides, 2 times 50 micrometers means your best accuracy that you can expect is plus minus 0.1 millimeters naturally. And these phenomena that you have here simply due to this generative process with the melt, they kind of tell me it's rather hopeless to hope that you can entirely avoid surface processing.
All right. We have more questions here. Let's see. Some in Spanish, but I think Jan cannot speak Spanish yet, or maybe you. Do you?
No, unfortunately not.
Let's translate. What's the influence of the shape of the pores and their sizes into the mechanical properties of the product? Do you have any?
Yeah. So the effect is mostly on the fatigue side of things. Think in terms of stress concentrations. If you have very, very sharp edges here at these pores, the balling pores, for instance, where you have unmolten particles and poor fusing of different layers, you have very high stress concentrations at the edge, which can aid or enable easy crack nucleation. So materials with this kind of pores, on the one hand side, the pores are very big because they correspond to the size of powder particles. So 50 microns or so, and larger. And their shape is very, very critical. So this kind of material you really want to avoid. This kind with the round pores, well, they are still rather big pores, but even cast materials do possess a certain amount of pores, so that's not untypical for other materials either. And they are at least not as critical in terms of shape. So I'd rather go for a process parameter set that has a few of those pores, rather than risking a parameter set that may have only a single or a few of those kind of pores.
All right, excellent. I have a general question. Maybe this ATM images you mentioned or you show, the atomic probe images, how do you produce them? Is the fifth cuts and then slicing on the TEM? How do you, yes, this is what you do in the,
yes.
How much time do you invest in these things?
That's something that our cooperators at MPIE next to us in Düsseldorf did, Philipp Kürnsteiner, Erik Jägel, and Dirk Rabe. So as you described, it's first by FIP, you machine a very small, very sharp tip with a diameter, base diameter of like 100 nanometers and a length of maybe 200 nanometers out of a specimen. That certainly takes a day, I would say, or half a day maybe per tip. Transfer them into the APT, which is an ultra high vacuum machine, basically with an energy source like a laser. In this case, the laser mode of the APT was used to evaporate the material of the tip starting from the top. And the material then dissipates in the vacuum, and there is a mass spectrometer that tries to measure the atoms that are atomized there. So it's a very tricky technique. We don't have one here at the DLR. It's rather an expensive instrument, as I understand, but I think it's also a very powerful one.
Yes, it looks very nice results you have. I think somebody else is trying to. Jennifer, please ask. Just write your question here. Let me ask you in between a general question. I have read, you know, some reports from American institutions, companies that are concerned about the cyber security, let's say. I could maybe mention the knowledge protection, because it's rather easy to produce files and then to send them per email around the world and print, let's say, a part or a weapon or whatever you want to print in the other end of the world. What do you think on that?
Yeah, that's a good question. Well, you know, from your days, you still know DLR. DLR is very, very critical on safety issues and software and anything that comes to that. So it's also a topic how to work with this kind of data. I know that our colleagues in Stuttgart, for a different project, the Cube with the fiber reinforced plastics, they are currently developing a system that's based on this Bitcoin system. I think it's called blockchain, so that you can attach authorship or incorporate authorship in designs, in design files and so on, in digital files. I don't exactly know how they do, but to me, this sounds good. Sounds a little bit like a solution for this problem. But yes, it's an open issue.
Yes, interesting. All right. I have a question here from the audience, from Enrique, maybe. Yes, well, a comment before that from Raimundo Arroyave, Professor Arroyave. He said cybersecurity is a major concern in the context of AM. Many people are trying to find out how to implement blockchains, exactly what you said, in the parts themselves. Yes, it's interesting. All right, Enrique now is asking, I think it's Professor Enrique from CIDESI. He works with powders and heap process. It could be simulated, the process, with a task to avoid further post-processing. I don't know, maybe he's asking about to simulate the hot heat treatment heap process before, to avoid post-processing of the 3D printed parts.
Oh, that's a very good question. I don't think I can really answer that. I can only speculate. But since HIP is not really a very new process, and it's been used for years and decades now, I would assume that there should be simulation tools for HIP processes as well, shouldn't there? I would guess so. I don't know.
I don't know either, but okay. We have a HIP process at CIDESI, so we can start collaborating on that, Kike, Enrique.
Sounds good.
Yes. Yeah, I must say that the CIDESI is yes, a relatively young group, but we're working hard and doing very fast progress. We have a lot of machines, installed machines, and I don't know if we printed already aluminum titanium alloys, but we are about to print also this kind of alloys. So this we should collaborate on that.
We would be very happy to.
So I don't see, what about, I don't know if I've missed any question from his, no, everything all right. So I think Jennifer, somebody who's called Jennifer didn't ask, let me open this one again. Thank you, says Enrique, all right. So Enrique was also in Germany, so he knows the German system, and he knows also German, so he can speak and communicate very fluently in German, so you can start talking on that.
Thank you. I think I remember him.
All right, you remember Enrique, all right. I don't see any more. Thank you, great talk, said Raimundo Arroyabe.
Thank you.
So I don't see any more questions also. Jennifer is not speaking, I don't know what happened. Well, I know it's late in Germany. It's about 7 o'clock, I think, or
it's
6 o'clock at least.
Yeah, it's approaching 8, but it's still fine.
8 o'clock, you see, it's late in Germany. So I am happy you found the time to speak about this topic to us. It's very interesting. Thank you very much again for your time and your knowledge on this. And I send you here from here a virtual applause, and keep safe and schönen ersten Advent nachträglich.
Dankeschön. Thank you very much.
And I hope we stay in touch to collaborate.
Yeah. Thank you very much, and I'm very happy that I have this opportunity to talk here. Thank you to the organizers. Thank you to Andrea particularly for the support.
Thank you so much. Andre, thank you so much. It was an amazing talk. Thank you again for being part of this seminar. We will keep in touch. Sure.
Yeah. Stay safe and healthy, and then we'll meet at some point.
Yeah, for sure.
Thank you. Bye-bye.
Bye-bye.
A los participantes que siguen conectados, vamos a pasar a un breve espacio de comida. Vamos a cortar la transmisión en este momento, pero se volverá a reactivar unos minutos antes de las 3 de la tarde para continuar con la sesión de la mesa redonda. En esta sesión de mesa redonda tenemos a 4 invitados nacionales: la doctora Patricia Zambrano, el doctor Horacio Canales, el doctor Omar López y el doctor Leopoldo Ruiz. Nos van a estar acompañando para una discusión a través de la manufactura aditiva en México y el progreso que se tiene para Latinoamérica. Los esperamos a las 3 con el mismo link de acceso. Pueden acceder. Nos vemos en unos minutos.